Here we are. I'm really excited to having you all at the opening of this year's RecSys Challenge workshop. Uh, it was a really amazing experience, and I'll try to describe it to you through these slides. As you can see, they are really elegant, and this is a clue that I've not done them. This is a work by Amra, and this is the first thing that I want to share with you. I want to personally thank all the other RecSys Challenge chairs for their effort during these months, because they've worked a lot, and without all of them, we won't be here now. So I want to thank Amra, I want to thank Gabriele, Nazareno, and Jesse. You are not seeing them now, but they are behind the scenes, and they are watching my back, and they are ready to act if something goes wrong. So now we can move to the RecSys Challenge. What is the RecSys Challenge? It is basically a game that started in 2010, and in which basically, based on the research in recommended systems, it is defined a new goal, a new problem, or new aspects of a known problem, and this is proposed to the community, but not only the academia, but also companies. So in this game, basically, the different companies and the best research groups in academia worldwide, they fight one against the other to reach the podium, to be the best in the world. And for this reason, it is really, really difficult to reach this kind of a goal. And the idea is that all these practitioners in recommended systems can fight and propose new novel ideas that could be used in academia and in companies. So to understand how we developed the RecSys Challenge during these years, we can analyze what happened from the start of the RecSys Challenge. At the beginning, we had a problem related to a context-aware movie recommendation, and this kind of contest has been developed during 3 different years. Then we moved to personalized business recommendation for Yelp users. And then again, we analyzed the problem movies, the movie tweeting. So we predict the amount of interaction that people receive via Twitter. Then we moved to item purchases and by analyzing click sessions. And then we moved to another kind of dataset that is called Sing. And in this case, using Sing, CrowdRec, MTA, you had to predict a job post a user will click on. Then the next year, the problem of job posting was completely modified, in the sense that now are the jobs that will be recommended to users, or user recommended to the jobs. And again, we move to a more classical kind of recommendation, but even more difficult, that is the music recommendation. But in this case, the goal was not to propose just a song or a list of songs to the users, but to propose a playlist continuation. And in this respect, we have an announcement to do. And the last year, we worked on the Trivago dataset, in which we wanted to build a click prediction model. Even in the, also in this case, based on sessions, user session interactions. And the announcement is that Spotify is going to release their dataset. As many of you know, during these years, many practitioners have asked to Spotify to release these big datasets that they realized for the RecSys challenge. And now they decided to do this. So here in this slide, you have some information that we will share with you with the different modalities, modes you can use to download these datasets and use for research purposes. But now we can move to the this year contest, in which the hero is Twitter. The Twitter team has realized an entire platform to let people to participate in the challenge, and they released the largest dataset ever with 160 million samples. And the task of this year was to predict 4 different kinds of engagement types: the like, the reply, the retweet, and the retweet with comment. But I don't want to say more, because in a while you will have the Twitter team that will explain you it in detail. So basically, you have seen just a portion of the story. You've seen that at a certain point we released the dataset, the 2nd of March. But before this date, we worked a lot with the Twitter team to define what to release, what will be the best features that we could use, and all the different aspects to make it possible. Then the Twitter team worked very hard to realize this and release the dataset. And at in that moment, the RecSys challenge of this year has started. Then we moved to the release of the test part of the dataset, and then the end of the challenge with the final leaderboard and the announcement of the winners. But the story is not finished, because behind the scenes we were working, and we were working with the participants that have won the challenge, to make them write down their approaches, to share them with the community. So they worked very hard to write the papers in a very little time, and then they submitted this paper. Not all the papers were accepted, and we will understand why. So after the notification, they received a lot of very important feedbacks that have been included in the final version that you can see. This year, the participation to the challenge was very high, with a very high number of participants, 1,131 different registered users in the competition. And at the end, only 20 teams have reached the test phase, in which they fought for the first place. And basically, each team was composed of almost 4 people. And at the end, they used an overall number of 127 different recommendation approaches. For the other part that we have seen, 12 papers were submitted to participate in this workshop, but only 9 were accepted. Now you can say, okay, the 75% or as an acceptance rate is very high, but it is not, because some very good research groups remained out of this workshop. And in a few slides, you will understand why. So now we can focus on the plan of today. The first session will be chaired by an unknown dude. Then I will give the word to the Twitter team, to Wenzi and Luca, that will explain to you all the different aspects of this dataset and of the problem that has been proposed to you. So this is a unique chance that you have to pose all the questions that you had in these months. Why did you do this? And why did you choose this kind of a contest, this kind of a problem, this formalization, this metrics, and so on? So please use your pen or pencil and start writing the question to the Twitter team. Then we have 2 papers in the first session. The first one is the 3rd place. So we start with an high-level work that have reached the podium. And then we move to another work that is the 4th place. So we have 2 very high positions here in the first session. Then we move to the 2nd session that will be chaired by Gabriele. And this session is very, very important because it contains the papers, not only the works, but the papers that received a very high rate on EasyChair, so by our reviewers. And you will understand in a few slides why this is so important. And the third session will be chaired by Jesse Smith. In this case, you will listen, you will hear the NVIDIA team that has won this year's challenge, and another very important paper, this gradient boosting paper. But also, we will show you, and will be presented, a paper that is the only one paper that is not about a single approach, but is an analysis done by Dietmar Janak and some of the NVIDIA team about the fact that we are wondering basically every day why, if these deep learning, deep neural network techniques are so trendy now, they are not consistently winning the RecSys challenge. So we will watch this analysis. And then you have another unique chance, because we created this panel with Dietmar Janak for academia, then Chris Diot and Maxim Volkov, and that are basically the 2 representatives of the first team, or the team that has reached the 1st place, and the team that has reached the 2nd place. And the Twitter team, in this case, Luca and Wenzi. So this is a unique chance to watch them talk together about the perspective that we have in our community. And also in this case, please start preparing the questions, because it is a really unique chance. And now, what I want is to start thanking a bit of people that have been very important these months. Most of all, I want to thank Yashar and Peter. They were our advisors. Without them, this year's RecSys challenge wouldn't be. And why? Because we had a lot of experience with workshop creation, with paper submissions, so on, and also with contests. But nothing compared to the effort and the bureaucracy that is needed to prepare a RecSys challenge. So their help was completely priceless. They were really, really important for us. And then we want to thank the Twitter team. For you, I can understand it, they are names. But for us, each of these names is associated with a face. Yes, not in flesh and blood because of the COVID, but during these months, we had at least a meeting every 2 weeks or every week to work very, very hard on the definition of the challenge, on the different problems that we could have on the platform or with the teams and everything. So they are our heroes for this year challenge. And we want to really thank Pablo and Yusara. Pablo Castells de la Universidad Autónoma de Madrid, en Spain, e Yusara Almeida de la Universidade Federal de Minas Gerais, of the Brazil Twitter team. They are the workshop chair. So you can say, okay, they were organizing all the workshops. But in this situation, it was a really, really hard work. And we needed a lot of help to prepare everything. And they were always present. And they helped us a lot. So thank you, Pablo and Yusara. And finally, who we want to thank is the dream team of the reviewers. Because here you can see that the people that have reviewed the different papers are basically the highest level researchers in our community. So we asked them to review this paper, and each of the suggestions has been incorporated in the papers. So this was a unique chance for the guys and girls that have worked on the RecSys challenge and then have written the papers to have these high-level reviews, high-level suggestions. So this is a reason why some of the papers have not passed their test. So, okay, here we are. So I'm seeing that Wenzi and Luca are warming the engines, so I will give the word to them. But before everything, I will say to you, thank you all to be here, and remember, if you have to pose any questions, please go down in the WhatsApp and you will see the related talk. Click on the talk on the right side. You can find a tab, session question and answers, and click there because we will be continuously monitoring them to find the new questions. So we can post them to the Twitter team and to the authors. So thank you all, and now I will give the word to Wenzi. Let me find here. Okay.
Hello.
And you are now in the spotlight. Okay.
Cool. Thanks. Let's see if I can make this to work. Right. Right. Can everybody see the slides?
Yeah, we can.
Okay. Cool. Thanks. Hi, everybody. My name is Wenzi. I lead the recommender system research team at Twitter. Today, I'm here with my colleague, Luca Belli, who is the tech lead for the Meta team. If I understand correctly, it stands for Ethical Transparency and Accountability of Machine Learning. Before we start, I also would like to mention that it really takes more than 2 of us to make the dataset available this year. In particular, we want to thank all the members in the team who joined us from across Twitter. The list includes, but not limited to, Alexandra, Ira, Frank, Ali, Yuanpu, Xiao, and Michael. I also want to introduce you to Bob, my dog, because I'm working from home at the moment, and he's just sitting next door. If you hear any loud barkings, that's from him, and I want you to link that to the face as well, so you're not too annoyed. Now let's go to the introduction. So in today's talk, I'm going to cover the motivations. Basically, why did we want to organize the challenge in the first place? The dataset, what did we actually release in our dataset? And then my colleague Luca will walk you through with the privacy considerations we had, what's our view on the results we had this year, and the limitations we found in this year's challenge. So why did we organize the challenge in the first place? First of all, as everybody attending this conference already knew, recommender systems are important parts of social networks and beyond, like e-commerce, etc. Its importance is universal for many tech companies today, like Facebook, Google, Amazon, Netflix, etc. Specifically for Twitter, it links directly to our mission. That is, we want to serve public conversation. Finding the right conversation for the right user at the right time is crucial for the success of that mission. And the recommender system is the tool that enables us to do that. Secondly, we believe large-scale standard benchmarks can help advance recommender system research. We all know that standard benchmarks like ImageNet were one of the key success factors of deep learning in computer vision. However, there's a lack of large-scale public social network dataset for RecSys, especially with content features. We believe Twitter provides an interesting set of challenges for the research community. And by providing this dataset, we hope to accelerate research in this area. Let's move on and talk a little bit about the dataset itself. So in this dataset, the task is to model 4 types of engagements. So these are like, reply, retweet, and code tweets. The main observed probability of the engagement actually decreases from like to code tweets, making the task more and more challenging. In terms of features, we have 3 main set of features. This includes the tweet features, where we had the ID of the tweets, the language or what types of link and media is provided in the tweets, as well as the most importantly, the raw text features. We transform them into bird tokens in the dataset. On the author side, we had the ID of the author, how many people they're following, and how many people how many followers they have, etc. On the reader side, we had similar features as the author, just mirrored. In the engagement, we also provide whether the reader is actually following the author, as well as when the engagement actually happened. Overall, we collected 200 million samples over 2 weeks. We used 160 million samples from week 1 as the training set, and 40 million used for validation and testing sets. We split data from the second week randomly into 2 20 million sets, one for validation and the other one for testing. This makes the dataset the biggest social network dataset released so far, which contains content features. However, we do want to acknowledge that this dataset is different from the internal dataset we use at Twitter. This is mainly due to the fact that to make this dataset available, we put a lot of thought into privacy considerations. Luca will take over the mic and walk you through about that in a minute. And he will also cover that what we learned from the results, as well as the limitation of the challenge this year. Over to you, Luca.
Okay, let me move the control to Luca. Okay. Okay, Luca, you can.
Cool, thank you. Hopefully you can see my slides. Yes. Cool.
Yes, we see them.
Thank you. So as Wendy was saying, I would like to talk a little bit about, start talking a little bit about the privacy considerations that we had while designing this data set. We wanted to provide a data set that is useful for the community and to advance research in recommender system. But at the same time, we want to respect privacy of our users. So the first thing to make very clear here is that everything that is in the data set is already public, in the sense that, as you might know, Twitter has an API, and you could connect to the API and download the same data that we already released. As a matter of fact, the data that is in the API is it's more rich than the one we released. However, I'd like to acknowledge the fact that the API is not free. And so in order for you to collect almost 200 million tweets, that has a monetary cost. Therefore, it will not be possible for everyone. Another thing we did was to obfuscate all the IDs of the users, tweets, etc. We do know that this is not an effective way of preserving privacy, as many examples in the past. However, we wanted to sort of disincentivize zero-effort misuse of the data set. In the same spirit, we wanted to make sure that people could use pre-trained NLP models and use all the richness that's in the text of the tweet without sort of having like the text of the tweet available so that someone could like copy and paste in a search engine and immediately find where the tweet was coming from. And so we thought that providing the IDs of the BERT tokens instead of the raw text could be like a good compromise, so that, again, you could still use a pre-trained BERT model, but it would be harder to sort of go back to the original text. An interesting challenge was how to provide negatives. When you're building a data set, you need some positive example and some negative example. The positive example are easier. It just means some users saw a tweet and they interacted with them. Could be a reply, a quote, a like, or whatever, right? All of these are public. So it's really easy for us to just build this data set. On the other hand, in this context, a negative sample would mean someone saw a tweet and they decided not to engage with the tweet. Now, what is the problem here? The problem is that we don't really, the fact if someone sees a tweet is not a public information. So had we just released, a set of negative created like that, we would have basically leaked the information of who saw whose tweet. And so what we did was the following. Instead of taking negative example, for each user, we took the set of tweets that were created by people they follow. We removed from this set all the positive examples, so the tweets that were engaged in, and we were left with a set of tweets that were not engaged with. We do not know if the user saw the tweet and decided not to engage, or did not see the tweet altogether. And that is what we put as negative samples for our data set, and that's we call them pseudo-negative. Again, because we don't know for certain that the user did see the tweet and decided not to interact. And the final interesting challenge was to sort of like keep the data set in sync with what's happening on Twitter. So as you know, on Twitter, you can delete a tweet, your profile can be made private. And we wanted to make sure to respect the choice of the user. So if a user would make their profile private or just delete a tweet, we wanted to make sure that our data set would reflect that. And so we had, you know, every so often our data set would sort of mirror what was happening on Twitter. And we also released you know, a diff file to make sure that everyone could keep their data set in sync with Twitter. Okay, let's talk a little bit about the results. So first of all, maybe I should spend a couple of words saying how we evaluated the submissions. So there are mainly two things: relative cross entropy with respect to a baseline we provided. And we provided a very simple, you know, naive model that predicts the average observed CTR in the training data every time. So nothing really smart. And then for each of the 4 engagement options that we discussed earlier, we another metric we used was the area under a precision recall curve. So as you might know, the NVIDIA team won by a big margin. Also, shout out to the NVIDIA team for donating all their prize money to the Blacks in AI Association instead of keeping for them. And so the secret for sort of their method is being able to do extremely fast feature engineering and model retraining. And that was, you know, a mixture of having a machine learning platform for recommendation system and very advanced hardware. It's interesting to note that all the top 3 entries really rely heavily on feature engineering, ensemble decision trees, and things like that. It reminds us a lot of the sort of landscape of computer vision before, you know, ImageNet and AlexNet. And so, you know, where back in the day, a lot of manual feature engineering were the key points to win this competition. And so this leads us for a couple of sort of like open questions for the community that we think are interesting and, you know, food for thought for the future. The first one is why NLP model seems not to have such a big impact on the final performance of the model. And the other one is, it seems that you know, deep learning does not really work that well for a commander system. In particular, why are not we seeing use of multi-tower, multitask learning models from industry research papers? It seems that XGBoost really outperforms a lot of these architectures. Which brings me to one of the sort of like limitation of this data set and of this challenge for us. The first thing I want to mention is, you know, as I said earlier, we are keeping the data set in sync with Twitter. And so if someone deletes a tweet that was part of the data set, the tweet will be also deleted by data set. Therefore, our data set is slowly shrinking. Obviously, shrinking very slowly at this point because people are less likely to delete older tweets than newer tweets, but it's a fact. And the other thing is that, you know, we only evaluated this submission on performance or accuracy and whatnot. But in production at Twitter, we have many other considerations. And one of them, that is really important, is latency. As you might imagine, everything has to happen really fast. And so, for example, approaches like ensemble XGBoost, they are not really an option for us to use because they would be too slow. There are many more details in our paper, so I'll invite you to check that out. And now, Wenzi and I are, I guess, happy to take any question, time permitting.
Okay. Luca, please stop the screen sharing. Okay. And now I remove you from the spotlight. I've not seen if there are any questions or not, but I want to start. I have a question. Are there any particular approaches that you have found that to be somehow unexpected? Some combinations that you had not considered before, or something like this?
Wenzi, do you want to take this one?
Yeah, I was going to say, I think one thing that we didn't realize would have a big impact, but afterwards it becomes quite obvious, is the adversarial feature selection, which is used, I think, in NVIDIA's entry and probably in second order third place. And the basic idea is that you would select features by training on a model that's actually trying to predict the difference between the training and testing set. And we didn't thought about that, and it seems to be quite a powerful method in terms of actually making sure the performance of the model generalizes.
Okay. Okay, and another aspect that that I wanted you to analyze, if it is possible. You've said that okay, the dataset for privacy concerns have to shrink, obviously, during time. But is that possible in some way, let's say, to let people to continue trying and proposing approaches that you can find useful in the next months? Because I've seen that little groups are interested in obviously continuing to work on the dataset and somehow remaining in touch with you, with your expertise, obviously, in the field.
Yeah, thanks for your question. I should actually have mentioned earlier, I guess, the dataset is still there and it's still available for people to use it for, any research or otherwise, purposes. If you go, I think it's Twitter, RecSys.com or something, it's still there. And so yes, it's still shrinking, and yes, it will keep shrinking. Obviously, the question is, are we keeping it forever, even when it's very small, or are we maybe at some point deciding to do, another one from scratch? And I do realize that, for having reproducible science, you need the same data set, but at the same time, we have to respect users' privacy decisions, and so I don't think that's something like we can ever, if a Twitter is deleted, it's also deleted from the dataset. But again, still there. Go, use it. Let us know what you find. We are always curious to hear from the community.
Okay, perfect. So we were out of time, so we need to move on. But please feel free to ask the questions at the end of the panel that we will have later, or obviously you can contact Wenzi, Luca, or I think any one of the Twitter team that are continuously working on these topics. Okay, thank you, Wenzi and Luca. And now I will enable Naomichi Agata with a staking ensemble model for prediction of multi-type tweet engagement. That is the work that reached the 3rd place in the competition. So let me find Naomichi Agata. Okay. And now I'm putting you in the spotlight. Okay, you can start. Enable the microphone, share your presentation and start.
Okay. Can you hear me?
Yes, we can.
Okay, let's get started. Hello, everyone. We are Team Wanted 3. We won the 3rd place in RecSys Challenge 2020. And in this talk, we will present our solution for the competition. Before we start, let me explain a little bit about Wanted 3. Wanted 3 is a Tokyo-based company, and we provide business SNS Wanted 3. In our service, we focus on reciprocal recommender system to improve company and user matching and user-to-user matching. For this challenge, we formed a team of 3 data scientists in Wanted 3. This is our first time presenting at an international conference, so we are very excited to have the opportunity to talk today. We would like to thank organizers for RecSys Challenge, RecSys Conference, and Twitter. If you have any questions while our presentation, please write them in session QA in Hoover. Okay. First, let me briefly explain this challenge. Because the previous presentation is introduction to the challenge, so you may know it already, but please let me repeat it. The task of RecSys Challenge 2020 is predicting engagements on Twitter. The goal is to predict occurrences of 4 types of engagement for each tweet and user pair. The target engagement types are like engagement, reply, retweet, and retweet with comment. The evaluation metrics are PRAUC and RCE, relative cross entropy. PRAUC is a measure metric, so you may be familiar with it, but RCE is an unusual metric, so I'm going to explain a bit about it. RCE is a metric based on cross entropy. It indicates the improvement of a model prediction relative to the naive prediction. The naive prediction means predicting the average engagement rate of the training dataset. For both metrics, higher values represent better predictions. Next, we will explain the dataset provided in this competition. Twitter provides us with the Twitter log data. The size of the training dataset is huge. It has more than 120 million samples. Each sample consists of 4 types of information. The information on the tweets, on the engaging users, on the engaged with users, and on the type of the engagement. The training data and the evaluation data are split over time. In the 2-week period, the first week is for the training data, and the second week is for the evaluation data. Next, we present the characteristics of the data set that we found in analysis and paid attention. First, we noticed that there are very few positive samples for some engagement types. Retweet with comment has the least number of positive samples, followed by reply, retweet, and like engagement in that order. As shown in the table, the percentage of positive samples of like engagement is 43%, but retweet with comment is only 0.7%. We also found the strong correlation between different types of engagements. It means that users sometimes make multiple types of engagements for one tweet. As you can see in this table, in the training dataset, 13.2% of like engagements occur with retweet engagements. Next, let's talk about the summary of our solution. We adopted an architecture of stacking multiple light GBM models. Light GBM is one of the major gradient boosting frameworks. It is fast and accurate. We needed a computationally efficient algorithm, and so we chose Light GBM. This is because the dataset is huge. In addition, we had to recalculate many times to comply with GDPR. We trained Light GBMs with various handcrafted features, consist of categorical features, network features, text features, and others. We will explain details of these features later. Each model is trained with negative undersampling and then ensembled with bagging. We use the stratified k-fold method for cross-validation folding. This is a summary of our solution, and next, we will explain details of each topic. First, we explain the architecture of our model. Our model uses a stacking architecture with two main stages. The rounded squares represent models, and the squares represent features. The first step is to create a model for each engagement type. We built 4 ensemble models for 4 engagement types individually. We call these models the first stage models. In this stage, we only use features that are independent of the target information. In the second stage models, we use the predictions of the first stage models as meta features for stacking. By using meta features, we aimed to create models that capture the correlation between engagements. In addition to meta features, we also use the features used in the training of the first stage models and features that are dependent on target information, like target encoding features. For example, to train the second stage models for like engagement, we use not only the first stage predictions of like, but also those of reply, retweet, and the retweet with comment. This is the key point of our solution. By using this architecture, we aim to capture correlations between engagements without losing computational efficiency. If we could use models that can predict multiple targets, we don't have to use such a complicated architecture. But such models, like neural networks, are generally computationally inefficient, especially in CPU. As I said earlier, the dataset is huge, and we need to use a model that is computationally efficient. We will get into the details later, but this architecture determined a lot of our training process.
Okay, hello, my name is Yuya Matsumura, a member of Team 123. From now, we describe the features we adapted to. First, we talk about categorical features. The given dataset contains 9 categorical variables, such as user ID, tweet ID, language, etc. In order to transform them into appropriate numerical features, we apply different encoding methods to each categorical variable. For low cardinality categories, such as language and tweet type, we use label encoding. On the other hand, for high cardinality categories, such as tweet ID and user ID, we use frequency encoding and target encoding. The GBDT algorithm divides samples according to the size of the feature values. Low cardinality categorical variables can be optimally divided in a few times, no matter how we transform them into numerical features. On the other hand, high cardinality categories must be transformed into meaningful numerical features, like ordinal features such as frequency of occurrence, in order to divide them efficiently. In addition, by creating frequency encoding features with not only a single categorical variable, but also the combination of categorical variables, we capture more complex relationships among them. For example, some active users search for interesting tweets by using hashtags. So we think we can capture the characteristics of active engaging users by using the frequency encoding feature with a combination of hashtag and engaging user ID. Second, we describe graph features. We create 2 types of graphs from a given dataset and use them to create features. One is the social follow graph. This graph is designed to consider relationships between users and their social influence. We create a directed graph where each node represents a user and each edge represents the relationship that a user follows another user. And we use flag features that represent whether each pair of users has first or second degree connections. And we also apply PageRank to this graph and use the results as features of the users for each node. The other is the like graph. This graph is designed to consider user similarities in terms of their preferences. We create a directed graph where each node represents a user and each edge represents the relationship that a user makes the like engagement with another user. We apply random walk with restarts to this graph and use the number of digits to engage with users nodes from engaging users nodes. Third, we describe text features. The features explained so far were based on users' attributes and behavioral patterns. We also think the engagement tendency is largely related to the text contents of the tweets. So we create features that estimate engaging users' preferences from the text contents of their tweets. We focus on 2 types of engaging users' preferences. One is a preference for content of the tweet itself, and the other is a preference for an engaged with user. To represent these 2 types of preferences, we create embeddings of contents of tweets and users. Then we calculate their inner products and use them as features. And for creating embeddings of contents of tweets, we use a global average pooling of the intermediate layers of the round multilingual BERT. And for engaging user, we create embeddings by using averaged vectors of the tweets that the users are engaging. And then the embeddings of engaged with user are created by using averaged vectors of the user's tweets. First, we talk about other various features. Here are some of them. First, we use the number of hashtags and media for each tweet as features, because we think the ease of engagement can depend on the number of them. Next, we use the following count and follower count of engaging user and engaged with user. In addition, we also use the following follower ratio, which is the following count divided by the follower count. We think this feature reflects the way users use Twitter and how influential they are. And we also use account age. That means the time elapsed since the user's account was created. This is because we think new users and old users have difference in the way of using Twitter. Next, we use user activity, features that represent the relative active time for each user. For a given action log date of an user, we count the number of other action logs of the user within n hours before and after the log. And we use main language, the most used language in each user's home timeline, and its ratio. Finally, we describe meta features. We use the predictions of the first stage models of each engagement as features of the second stage models. Since every engagement is highly co-occurring, the information on other engagements is important to predict one engagement. We also take the aggregation of the predictions by categories, such as user ID and tweet ID. We think they can express the tendency of the engagement in each category.
Hello, my name is Shuhei Goda. I will tell the rest. In this section, we will introduce some tricks for training the model. Because the dataset is so large, we use bugging to create high-performance models efficiently with small training dataset. Small training dataset for each model are generated by different sampling patterns, and then take the prediction averages of those models. We describe the sampling process to obtain a small dataset. As the target is imbalanced, we apply negative undersampling to reduce the data size and make the number of positive and negative samples is equal. However, targets such as like and retweet engagement still have a huge amount of data even after applying negative undersampling. In such cases, we apply random sampling to make the data size even smaller. The predicted probabilities are based on the downsampling space because of negative undersampling in training. It is important to predict the engagement probability since RCE is one of the metrics of this task. Then we recalibrate the predictions based on the following equation, where P is the prediction in downsampling space, and W is negative downsampling ratio. By this recalibration, the smaller W is, the smaller P is. In this section, we will discuss how to create cross-validation. We use stratified K-fold so that the ratio of positive samples of retweet with comment engagement in each fold is equal. We use the same split for all targets. If we use different splits for different engagements, the negative influence of the leakage due to meta features and target encoding gets bigger. This is because each engagement is not actually independent, but has a certain degree of correlation. Considering the calculation time, we set the number of folds to 3. Finally, we will discuss the results of our experiments. All experiments are conducted with these resources. We show our final results. Here, we compare the first and second stage models to evaluate the effect of stacking. The second stage models outperform the first stage models on both metrics. As you can see from this table, PRAUC and RCE of the second stage models are higher than the first stage models. This result supports the effectiveness of our stacking architecture. However, the problem is that the second stage models are overfitted. The difference between the training and validation score of the second stage models is larger than the first stage models. Sorry. The first stage models are designed to be robust. We don't use target-dependent features for these models. They also use features of which distributions of training and test are almost the same. As we expected, the difference between the training and validation RC is small, at 4.251. Compared to the first stage models, the second stage models have a larger difference of 6.048. We finally considered that it was not a problem as both the training and validation scores improved. From experiments, we found that the degree of overfit of the second stage models actually depends on the number of training data. In this section, we will talk about the relationship between them and how to determine the number of training data. In the second stage models, the larger the number of training data, the worse the validation score. The first column of this table is the number of training data. Let's look at the like engagement where this trend is evident. With the number of samples of 100,000, the like RC of the validation is 24.728. But if we increase the number of samples by 20 times and train with 2 million, the RC is 22.991, which is much worse. Since the targets are highly correlated between different engagements, we believe that the use of meta features and target encoding tends to overfit, and this effect is likely to be more significant with more training data. Based on this result, we decided to reduce the number of training data in the second stage models. We set the number of training data to 100,000 for like engagement and 1 million for all other targets. Because like engagement is more sensitive to data size. Although the number of training data for like engagement is severely reduced, we balance the robustness and accuracy by increasing the number of bagging models. So this slide concludes the focus of discussion today. We introduced the third place solution for the RecSys Challenge 2020 by Team Wanted3. We used two-stage stacking models to efficiently and effectively capture the co-occurrence between engagements. We thank the organizers of the RecSys Challenge and Twitter for the opportunity to participate in this interest competition. If you would like to know the details of our implementation, please refer to the code published on github.com. Thank you for listening.
Okay, and thank you for your presentation, Naomichi Agata. Okay, please stop sharing your screen.
Okay.
Okay, now I would remove you from the spotlight. Okay, and congratulations for the third place.
Thank you.
And I have a couple of questions that I want to pose to you. Let's start with the first one. You have combined several kinds of different kind of features in your solution. You use categorical encoding, graph features, text features, numerical features, target encoding, and meta features. Okay, and this was really interesting from my side. But do you have any idea of what are the features that add more impact on the results that you obtained?
Because of the computational resources limitation, we could not try many experiments using, for example, BART features or some other text features. We use text features with a simple naive preprocessing. So yeah, so if we have more resources, we wanted to use text features much more.
Yes, but among the features that you used, okay, which ones are the features that, yeah?
It is.
In your opinion, obviously.
Meta feature.
Meta features.
Meta feature is very big. Yeah. Especially aggregating meta features by user ID or suite ID, it is really impactful.
Okay, thank you. And the second question is more or less related to this. You adopted several sampling strategies, like recalibration, the sampling strategy itself, and the bagging. But you used all of them together, or do you have tested other combinations, like two of them together, and so on? And in this sense, do you have discovered any interesting insights, or was one of them particularly helpful, or only all of them together?
Insight. In our experiments, we observe big overfit with large training data sets. So we have to use bugging. So bugging is required for us, and recalibrating the predictions are effective to the leaderboard. So it is important, we think, but we don't have many experiments because of the computational resources. So we don't have anything to say about that. Sorry.
Okay. I thank you for your presentation, and now we can move to the other paper. So bye, Naomichi. Okay. Now I've seen Samit Sidana here. Okay. Now I'm making a cost. Okay. Please, Sidana, enable the webcam. Okay, perfect. And okay, now I'm putting you in the spotlight for everybody. Okay. And you can start. The paper that we are going to listen to here from Sidana is a combination of classification-based methods for recommending tweets. And this was placed at the 4th place in the overall competition. So congratulations, Sidana, and please start.
Thank you very much. Welcome to my presentation titled A Combination of Classification-Based Methods for Recommending Tweets. And I want to thank Twitter and RecSys Challenge organizers for organizing this competition and giving the opportunity. So these were the details of the challenge results which I obtained. The goal was to determine the probability that the engaging user is going to engage with the content of the engaged user. And my team name was learner RecSys, and overall score was 20. And engagement scores are as shown in this table. My position was 4th, and code is available on the GitHub publicly. And if you have any questions, just send me a message or an email. I would be happy to answer all the questions and to make it reproducible. So these were the overall dataset statistics, and so I mean it was a large-scale dataset, and it took a lot of time to load also. Number of tweets in the training were 150 million, and validation set had around 15 million and test set around 12 million. And it also had a user cold start problem with a lot of new engaging users and invalidation and test. The main challenge for me was also about number of languages, how to represent these languages on a common dimensional space so that to be able to recommend properly. And all these numbers denote the original numbers, and they do not reflect the tweets that were being removed to preserve user privacy. I mean, that was also a new thing for me, the GDPR and things. And these are I created a validation set and training set from the training set given, I first sorted on timestamp and divide the first and took the first 90% as the training set and the remaining 10% as the validation set. I also ensured that all days were present in both training set and validation set, because in the validation set which was given to us also all days were present, and I wanted to match the distribution as far as possible, so that all the results on the validation set match on the validation set given. Mostly I succeeded in doing that. After dividing the training data into train and validation, I was left with the number of tweets as shown in the table, and it was around 133 million tweets in the training set which I obtained, and 14 million tweets in the validation set which was divided after I divided. The metrics given in this competition were relative cross entropy and area under precision recall curve. First, I started with a very simple priors baseline. I computed the probability of the respective engagement or implicit feedback, and I used the following formula. I took the number of tweets in the positive engagement and divided by the total number of tweets. And that was a very simple baseline, and it was already performing well. So reply had a prior of 0.028, and the highest probability of engagement was for like 0.439, and retweet with comment had the lowest prior probability of being done. It was 0.008, making it the most difficult engagement to predict. Second baseline I tried was simple content-based recommendations using bird embeddings. I represented each tweet with a 760-dimensional bird embedding vector, and I took that vector and I computed the user vector by averaging all of the users' positive engagements. So that then the user's vector was the average of all the tweets he interacted with. And then during the prediction time, the score of the user tweet pair was the dot product of the user vector and the tweet vector. But this did not perform very well, partly I think because I did not do proper normalization. In retrospect, I could have done some proper normalization. It could have performed well. It gave a very low PRAUC and RCE on reply and a drop test method. Now the problem which was given to us was a natural binary classification problem. We were given positive samples, tweets which user engaged with, and the negative samples which were sampled randomly. So this was natural binary classification setup. So I started using the methods which are meant for like this binary classification, which have stood the test of time. I started with factorization machines, which was proposed by Stefan Rendel in 2010, and it's a hybrid between classification-based approaches and factorization-based approaches. Its loss is given by, as shown in this equation. The first term is logistic regression term, and the second term is the factorization term. Basically, it factorizes all the features and all the features which we input, and it factorizes it. It runs in linear time, which is a super fast method, and Rendel proved it how to do that. And one of the extensions of factorization machines is field-aware factorization machines, which was proposed by Juan et al. In 2016, and from then on, it has been used to win a lot of recommendation challenges. And the only difference between factorization machines and field-aware factorization machines is that the field-aware factorization machines learns the different latent vectors for different feature interactions. And field-aware factorization machines works really well when we have a lot of categorical features, and factorization machines works well when we have the mixture of numerical and categorical features. I also use for text representations, I used fast text embeddings, and fast text is a framework given by proposed by Facebook, and it basically I took these embeddings and added them as features to my models. So I first converted the tokens which we were given into raw text using Hugging Face library, and then I converted from text to embeddings using fast text library, and each text, each tweet was represented as a 20-dimensional vector, and each language had its own embedding, and that was because Facebook provides a different model for each language. This is what is present in fast text, and aligning these embeddings into a common dimensional space is a research problem in itself. For feature selection methods, what features are important for these models? I applied Gini index for categorical features and lasso for numerical features. My best model for reply was factorization machines on the leaderboard, and I used these features, which again was used using Gini index and lasso. But on the validation set, my best method was field-aware factorization machines, and the PRAUC I obtained on validation set was as shown in these tables. For retweet and like, I used various methods, including these two, and the best model was field-aware factorization machines. I used these features and added 20-dimensional fast text embeddings to the existing features, and the results are shown as shown in this slide. For factorization machines, I obtained a PRAUC of 0.421 and RCE of 18.47. With field-aware factorization machines, I used the base fields plus fast text embeddings, and that gave a huge improvement of 0.49 and 25.7 of RCE. And similarly for like, I used the same features and added fast text embeddings. These for like and retweet, they were very dense engagement, so this seemed to work very well. For retweet, quick comment, I faced, I was facing a lot of difficulty to improve any sort of matrix on this feedback, and it was really sparse, with 0.8% of total tweets getting the positive engagement on this training data. So for a retweet with comment, again, I did feature selection using the methods I described before, and these were the features which gave me the best results. I tried various methods and various feature combinations, and the best method which gave the best results was was with these features. But in the end, the best results were on the leaderboard were obtained by a simple non-personalized baseline, and that was a bit strange, but that was how it went. I did a rigorous parameter tuning of all the models, and so these are all the parameters which were like after doing all the parameter tuning, these were the results I obtained for the parameters. For the implementation, I used a simple library which was provided by the original author himself, and it's written in C++, super fast. And for field-aware factorization machines, again, I used the implementation given by the original authors, and it also provides a highly parallel training. For the machine, I used AWS instances having Ubuntu 18.04 and having 96 cores with 192 GB of RAM. For BERT, I used Hugging Face library, and for fast text, I used fast text library provided by Facebook. For future directions, I could have used topic models for the features and add those features. I did use some topic models for this, but the main challenge I faced was how to represent the topics in different languages as a single vector and add them as features. And then with the machines I had, I couldn't add all the different language topics into this thing. I could have also added content-based recommendation scores from BERT in these approaches. And I also wanted to apply BPRMF and all the learning to rank based methods, which I didn't get time to do it. And all the deep learning methods, I couldn't apply them to this approach. Also, I mean, after listening to the yesterday's tutorial, I thought I could have applied the combination of all the features, and that I didn't do it. I think that would have given huge boost to the performance with these models. Thank you for your attention, and thank you for the organizers and Twitter once again to give opportunity to participate in this competition.
Thank you, Sidana. Thank you for your presentation. Okay, so please remove the screen sharing. And now I'm removing you from the spotlight. And even here, reading your paper, I had a couple of questions that I want to pose to you. And a couple of considerations. The first question is related to the formula, basically, that you use at the beginning for predicting the score of a given user tweet pair, in which you compute the dot product of the user vector and the tweet vector. Basically, this is a vector space model formulation. And you've seen that this approach was not working. And you wrote that this could be due to an improper scaling. So I was really curious to know if after the end of the challenge, you have tried or not to rescale it in a proper way and obtaining different results. This is the first question.
Yeah, that's a good question. Actually, I haven't tried, but I mean, due to lack of time. But that is something I'm super interested to try out, and I really think that it has got a huge promise to improve the results. That was a bit disappointment for me in the beginning, that these I had a very high expectations that this method can perform well. But I think this was also a bit due to but I may be wrong. It could have been but maybe that let's not go there. It could have been due to a ranking metric. It could have performed well. I think it was due to normalization, and I would be super interested to see how it goes. Yeah.
Okay. And the second question is related to these basically two kinds of recommended system that you use. On one side, you have this content-based try that you have given, and on the other side, you decided to use these collaborative filtering methods, basically, with field factorization machines. Have you ever considered, and if yes, why you have not tried it, to hybridize these approaches in some way? There are several ways, but that could be a strong opportunity to enter the first three.
Yeah, that's again a very good point. I was thinking to hybridize. I just didn't do it because of lack of time. And I mean, I spent a lot of time in improving feature engineering and with the field-aware factorization machines. So one thing I was wondering during the competition was like adding all these features with topic models and that took a lot of time, and I didn't get the time to hybridize this. But I think that like even hybridizing the content and collaborative is one of the future directions I want to pursue and see how it performs. Maybe I could hopefully submit this paper or something like this. Yeah.
Okay. Perfect. Thank you. And now I have a couple of considerations about the future directions that you said. Because, for instance, it is known that if you decline the factorization machine at the second order, you basically obtain matrix factorization. So the interesting thing is to see what happens when you apply BPR. It is a pairwise learning to rank approach. So this will be interesting. Is BPR able to outperform this kind of methods? This could be really interesting, yes. And the other aspect that I consider interesting is your mention to neural collaborative filtering, because as you know, there is a debate in these months between basically Randall and E about the performance of the two methods and the right way to basically factorize. So yeah, I think that this will be a debate that will interest a large part of our community, and it was very good to watch the presentation of the Randall's paper at this year's RecSys. Yeah. So thank you again for your presentation.
Thank you.
And I want to thank also all the attendees, because now we are running out of time for this first session, and we will see again in 1 hour, and we will watch a session in which there is the second place of the competition, and on the other side we have all the papers that have reached the highest ratings on EasyChair by those reviewers that you have seen. So there are all very, very high level papers and works. So I'm very curious to watch them. And a final thing, I will ask all the authors of the papers to ask questions to the competing papers, competing works, competing teams, because it will be really interesting for another attendant to see what the people that have worked so hard in the competition think and suggest to the other teams. So thank you again to all of you, and we will see each other in an hour in a session that will be chaired by Gabriele. Okay, to the chairs, we will see, I think, in half of an hour to prepare everything. So see you later.
Also present and moderate this session. So first of all, a reminder for the audience. So in order to ask questions to the presenters, you have to go to the agenda in WOVA, enter the RecSys Challenge Workshop, click on the specific subsection of the paper and post the question in the session Q&A tab. Then I will read it for you. So we can start immediately. So Ali already shared the screen, so very good. So the first contribution is the one of Sayed Ali Al-Hosseini, and is presenting his work entitled Engaging with Tweets, the Missing Dataset on Social Media. So please, Ali, the stage is yours.
Yeah, thank you. Good morning, good evening, and good night to everyone based on which time zone they are joining us today. And I'm very happy that we participated in this challenge. I would like to thank the organizers of the challenge and also Twitter for giving access to this data. And finally, I would say congratulations to the winning teams, and it's well deserved, I would say. Before I start, a little introduction about myself. I'm Ali Al-Husseini. I'm second year PhD student in Potsdam University here in Germany. I'm also a researcher at the Hasse-Plattner Institute. My research interests are focused on information diffusion on social networks. I've been working on bot detection. So basically how synchronized accounts have manipulated, let's say, or how they can change the course of discussion on social media. And I've been interested in working on deep learning methods on graphs. So in this slides, I will give a very brief introduction, and then I'll dig into the observations that we saw, the patterns that we saw in the data set, the model we used, the results, and finally, what I intend to do with the data set as in the future works. So I would say anybody who's working in the social media domain understands that it's quite hard because it's a very critical, when it comes to working with this kind of data on social media, it becomes very critical, and the privacy issues become a concern. And this is a very big step, I would say, that Twitter has released such a data set. Although I'm also looking forward for the roundtable at the end because there are still questions regarding privacy that I think should be asked. I won't go through the data set description because in the previous session it was talked deeply about it, and we all know which features and which data was available. So basically, the data set, the tools that we used to work with this data set, we worked on a Spark cluster and basically the PySpark library and through a Zeppelin notebook. And all these codes are available on my GitHub. So I would go into the observations. The first thing we basically saw from the data is the engagements in an hourly basis. So you can see that 75% of the engagements were like, 20% were retweets, and 4 to 5% were replies, and less than 2% were quotes. So this is like the flow of information that is coming into the system. And I would say this shows that because one of the metrics that we for the evaluation was the RCE. So any simple model would be, if you were to come up with a very naive model that can predict 75% of the time if somebody is going to engage, it's going to be a like, you will have a very basic model. And this observation can show that if you want to have a better result than a simple base model, you have to be better than this. The second observation that we had was the follower and following distribution. So in most social media phenomena, we see that there is this zipped distribution. So there are a few people that have lots of followers and a vast majority that have a low number of followers. This is something that is quite natural to see in social, like social accounts and in friendship relationships. An interesting thing that we saw was in the following count. So in Twitter, you can choose who you want to follow, but you can't. You can choose who you want to follow, but you can't choose who's going to follow you. And basically, one of the things that we observed was this spike in the following distribution. And this was of interest to me because I was like focused on bot accounts. And you can see that there are some accounts that in an abnormal way are following lots of different accounts. And I would say this data set for me was very interesting because you can focus on whether these bot accounts, how are they tweeting, how are they engaging with other tweets. And also we considered bots that were in this let's say oval as a feature for the model. The third observation we saw in the data set was the hashtags that came into the system. So there are 2 points that we can see from this chart. Number one is that if basically from the different hashtags that are available in the system, you will see that some of them get more attention and basically become a trend. And another thing is that if some hashtags are able to make it to the top, you will be able also to remain in the top. So also a phenomenon known as the rich get richer. The same, I would say, chart was available for the links that were shared. And again, we use this as to identify the trending hashtags or the trending links and consider these as a feature to better distinguish the different types of the different types of features. So at the end, we came up with different features, like for the tweet features, we considered the TF-IDF from the text, the different types of the tweets, and basically is the hashtag that is going to be shared at the top or not? Is the link that is shared from a tweet is in the top or not? And for the users, also the same thing. But for the we use the account year, whether it's verified or not, whether it's a bot or not, and the way we decided whether it's going to be a bot or not is if it's in the abnormal part of the distribution. And also we considered the following and followers based on like 50 percentiles to differentiate different types of users. So eventually the model that we used was a very simple binary classification with gradient boosted trees. So we had the training data set, we filtered the data set based on unique tweets, and based on the features that I said in the previous slide, created the model, and also the same thing for the users. And for each different engagement types, we trained 4 different models to predict the like, the reply, the retweet, and the code. The results that we got, I would say, was not that much good, but what we can see is that basically the less data that you have, it gets harder to predict. Like the models that wanted to predict for codes was much harder than for predicting likes. As for future work, I would say I would be interested, because this data set also provides the timestamps. What I'm looking to work on is to see how highly synchronized accounts, is there a correlation between the synchronized accounts with their engagements and also the distribution and the abnormal part. So this is one of the things I'm looking forward to work on with the data set. Another thing is the open benchmark graph. I know that in Stanford, this website has been, it's a new thing that they're working on. I know that they were talking about releasing the test data set. So if it's possible to put the training, the validation, and also the test data set into this framework and as a benchmark, I think it will be interesting. And that's pretty much it. If there's any question, I'm happy to answer.
Okay, thank you, Ali. So please unshare your screen.
Mm-hmm.
Okay, good. Thanks for the nice presentation. So I guess I have a couple of questions for you.
Yes.
So first of all, you did a nice analysis on the statistics of the dataset, for example, in order to identify the hashtags, duration, and these bots. So I was wondering if you did also an analysis on the aggregated feature, let's say their impact on the final prediction of the model. So did you consider to do something like this?
If I got your question correctly, you're asking me whether I did an analysis on the aggregation of them?
No, I mean on their final contribution, so their importance, their impact in the final prediction. So either these were features from the original data set or the one you aggregate your compute on your own.
Mm-hmm. So what I tested, I remember the features that I first chose, like for the bot, we were considering the abnormal part as a specific feature, but also the 50 percentiles. And once we uploaded it without the bot and again with the bot, so we saw an improvement. But I would say whether we went through exactly observing the result on a k-fold method, we didn't go through that, and it would have been a better thing to do so.
Okay, clear. So following up on this bot analysis, so I was curious, so how you decide that this abnormal distribution was, I mean, a matter of bots, and what is the rationale in using it in the prediction? So why do you think this will improve your model?
That's a very good question. I would say when I was not expecting to see such a abnormality in the distribution, and when I did see the spike, it reminded me of a paper. I think it was titled Catch Sync. Basically, Catch Sync is a paper from that they show that if you see this kind of abnormal thing in the out degree distribution, it's an indication of bot accounts. And so I was interested to see how, if you remove these accounts, how will it be different for the engagement?
Okay, so you removed the bots. You didn't use it as a feature.
So I used it as a feature, so it will be basically splitting it and looking at the bot accounts in a different way.
Okay.
Mm-hmm.
And finally, you mentioned in your future work this graph, link graph released by Stanford. So could you comment a bit further on it?
Yeah. So I would say the Open Benchmark website, what they are doing is gathering graph databases and basically coming up with a framework that can be a standard framework, so everybody can implement their methods on this standard platform. So I think it will be very nice if it could be possible to put this data set there, and everybody can compare their different methods based on this platform.
Okay. So yes, I'm out of question, and yeah, Yeah, I think we can conclude it by thanking you once more. So thank you, Ali, for the nice presentation.
Thank you very much.
And so next one presenting will be Kevin Shen. So I'm very glad to announce him, given that he's presenting the work that achieved the second position in our challenge. So please, Kevin, take the stage.
Thanks so much for the introduction. Can everybody see my screen all right?
Yes, perfect.
Okay, perfect. So I hope everybody's having a good conference and has enjoyed this workshop. My name is Kevin. I am a machine learning scientist at Layer 6. So Layer 6 now is part of TD Bank. So this is Toronto Dominion Bank. And I will be presenting our solution this year on the 2020 RecSys Challenge, where we got second place. So this year's work is in conjunction with Cohere.ai. So the names of some of the members of this team are listed here. And so our work in conjunction with Cohere, so Aidan Gomez, who is one of the co-founders of this company, he is actually also one of the original inventors of the transformer model. So it was very helpful to have their team on board and in kind of working out this year's solutions. And as I'm sort of foreshadowing, we did use transformers in our final solution. So for those who don't know us, Layer 6 is a boutique machine learning firm based out of Toronto, Canada. We're about 50 people now, and we do a wide range of research from RecSys. We publish in NeurUps, CVPR, and we even had a dabble at Nature. So we're a very diverse team. And we sort of participate in the RecSys Challenge almost every year. And when we do, of course, it's a fantastic opportunity for us to work on these very interesting, very massive scale data sets. But we also kind of go into these challenges with the goal of trying to improve ourselves as machine learning scientists. So we're usually, we're focused on trying to, really derive out some skills or learnings from each year's challenge. So then we can then kind of take them back into our own projects at our company and apply them there. And so when we kind of approach these challenges at a high level, we try to approach them in a very principled and sort of novel way. We try like principled techniques. And in the next 20 or 25 minutes or so, I want to share our learnings this year with you. So the first thing is I will try to convince everyone here that for this Twitter dataset, that deep learning can be actually very effective. And in particular, I want to emphasize that deep language models can be very effective. And maybe the key marker of this dataset is that it's a hybrid dataset, meaning we have both tabular features and also, of course, the tweets. And that sort of enables us to use these deep language models. So I think maybe if we think about very large tabular data sets in RecSys systems, we think about XGBoost or LightGBM or any sort of GBM model as the de facto model that we kind of fall back to. But hopefully we can show here that both deep learning and XGBoost, it's not a question of or, it's a question of how should you use them together. And indeed, when we use them together, we found the best performance in our model. And I think I just want to say that at the end of the day, maybe the important thing to take away from this presentation is hopefully I can share some of these learnings and skills, and hopefully these insights will be valuable for you to take back to your own projects and apply them there and improve your own systems. Okay, so here's basically the chapters of our story for the next 20, 25 minutes or so. So first, I'll focus on how we did this year in this challenge, and I will talk a little bit about a high level what's different about our approach. So the base of our approach is this very highly scalable GBM, and in particular, we use XGBoost. And then on top of that, we used a deep learning system to give us that extra edge in performance. And then the last thing I'll touch on are the benefits of using a deep learning system. And here I'll specifically talk about explainability, and we'll look at some concrete examples of predictions our models made. So here's a look at the final leaderboard of the competition. The metric of interest is AUCPR. And here I've listed the final scores for the 4 engagements: reply, retweet, comment, and like. So as you can see, we placed second this year. And in particular, I want to draw your attention to the fact that if you look at our score and the next best team score, so team in 3rd place, there's actually quite a large gap. So we, I think, convincingly beat the next best team in AUCPR across all 4 engagements. And if I draw your attention to the reply engagement, the gap is particularly big. So this is a difference of about 3 AUCPR. And if we put that in the context of how close and these RecSys competitions are, so if we think back to last year's competition where the top 3 teams were separated by about the 3rd or 4th significant digits, 3 out of 20 AUCPR is actually quite a bit. So I think there's quite a convincing gap here. And usually when there's such a, I guess, significant gap between the final solutions, that usually means there was a fundamentally different approach. And the sort of different approach that we took in our solution was to use these very massive deep language models. And just one other thing I want to point out in this leaderboard. So props to NVIDIA for getting 1st place. And if you look at their score, there's actually a very large gap as well between them and us. And we believe that's because they were able to find a leak in the dataset, and we did not use this leak in our final solution. Okay, so at a high level, this is our final model. So sort of in one sentence, it's a linear ensemble of XGBoost and a deep network. So intuitively, what's going on here is your XGBoost is in charge of understanding all the tabular and statistical features. So I think this is where we might be very similar to a lot of the other teams. So you're understanding tweet features, creator features, user creator, user tweet, and user creator CF, standing for collaborative filtering feature. And I'll touch on in a little bit what that is. And also intuitively, your deep network is in charge of understanding the text, both at a structural and also a semantic level, or any other pieces of text. So the previous tweets that the user has engaged with, and also the hashtags. And yeah, so together we put them into a linear ensemble and we predict each of the 4 engagements. Now there's some nuance here because you might notice I put an arrow from the inputs of the XGBoost into the inputs of the deep network. And I will just describe this in a moment, why. So it turns out we found that you can't really just throw a deep learning system that only knows about text into an ensemble with an XGBoost system that only knows the tabular data. We found that in order for the deep learning system to contribute effectively to the linear ensemble, it needed to actually match and then succeed the performance of XGBoost. So maybe the most natural way for us to achieve this is we actually put the tabular features into the deep network as well. So that's what I'm showing here. So first we have this XGBoost system, and we're going to develop a set of predictive tabular features based on that. And then we have a deep language model here you see on the right of the image. And this is in charge of embedding the tweets into a fixed sized vector. And then given these 2 inputs, we then pass them into a multi-layer perceptron that combines and understands both. So in the next 3 sections, I will be touching on each of these 3 parts of our model. Right, so the first part, the foundation of our model is an XGBoost model. And this model is the model we use to sort of rapidly iterate on tabular features. Now, maybe one very sort of natural question here is, why did you use an XGBoost model to iterate on features rather than just simply using the MLP? And that's because XGBoost is a lot easier to train and it's a lot easier to tune. And it's actually a lot, usually faster to train as well. So we found it to be a lot easier to use in sort of iterating on these features. When you're using deep learning, you have to worry about all the different types of features like categorical, ordinal, and stuff like that, and how you're going to encode them, and that complicates the process. So XGBoost is sort of the ideal algorithm to use for finding effective tabular features. So just a little bit of sort of information on how we approach XGBoost at layer 6. So of course we know this data set is extremely massive, extremely powerful. We're looking at 100 million training samples, and which is about 200 gigabytes in size, and for our data set that we end up using. And this is very challenging, right? So we at layer 6, we have a proprietary Java framework that allows us to work on this very big data sets using in parallel across a lot of different cores. So I guess just to toot our horn a little bit, we were able to get around 100% CPU utilization around at 40 cores. And this allowed us to train models very quickly and iterate on these features very, very quickly. So in the end, we've tried about thousands of tabular features. And in the end, we found 467 that were very effective in making the predictions. And so here's a quick look at how we would have stacked up if we had only used XGBoost. So here I'm showing in the top row our XGBoost performance on public leaderboard and the third place team's performance on private leaderboard. So it's not apples to apples. So we're comparing public to private, but I just want to give everybody sort of a rough sense of where we would have placed. So these scores, I think we're doing slightly worse. So I think if we just think about it a little bit, we would have placed somewhere around 4th or 3rd, like probably 4th, or in that sort of ballpark range if we used only XGBoost. And deep learning was what got us that extra performance boost to get into 2nd place. So for those who are interested, here's a quick look at some of these example tabular features just for concreteness. So there's some obvious things in the data set, like how many followers does this user have? How many people is this user following? We also looked at some pieces, some word pieces or in the sentence. So these are either words or punctuation or something like that. So in the top row, you see an example. I hope it's not blocked by the speaker column here, but it's supposed to be basically just circling the exclamation marks, and we look for symbols like basically exclamation marks in the text and the tweets themselves. We have something called user tweet features. So what this means is we try to build up a profile for a user, and the profile basically consists of previous tweets that the user has engaged with. And then you can imagine we do some sort of comparison between the current tweet we want to predict on and the user. So this can look like sort of comparing words or symbols or tokens between the list of previous tweets and the current tweets. Finally, there's something called a user creator CF or collaborative filtering feature. And this simply means we ran a CF algorithm on the user and the creators. And then we took the probability of that model as an input into the XGBoost. And so just to clarify, user here, we mean the engaging user. So the person who is potentially going to engage with this tweet. So the second part of our model is this deep language model. And what's going on here is the input is a tweet in the form of a string. And then the output needs to be a fixed sized embedding vector that's going to go into a multi-layer perceptron. Here's a look at the performance of our model using these embeddings. And I guess what I'm trying to emphasize here, so the top row is the performance of our XGBoost model. The bottom row is the performance of our deep learning model that uses the embeddings. And what I want to emphasize here is that there's actually a very significant performance increase when we use these tweet embeddings. So for example, for reply, it's almost 2 AUCPR. Okay, so this slide is very busy, so let me kind of guide everybody through it. So the two deep language models we tried were both transformer models. And in particular, they were BERT and XLM Roberta. So for those who, I guess, haven't delved into transformers too much, XOM Roberta, it's sort of basically just a bigger version of BERT. You can think of that being as just being a higher capacity model. In particular, we used the multilingual versions of these two models. And what I'm showing here is the general workflow of these large transformer models. So you have two phases. In the first phase, in the training phase, or some people call it a pre-training phase, you train these transformer models on a very large corpus of text in an unsupervised way. So this data set is usually the Common Crawl data set, or it's the Wikipedia data set. And the loss you use is called the masked language modeling loss. In the inference phase, which is the phase we care the most about, you take as input a tweet. Here I've pulled sort of an infamous tweet from Elon, and you pass them through the transformer to get a fixed size embedding. Now, there's obviously a problem here, right? So usually the text you pre-train these transformers on looks like this on this Wikipedia entry here on recommendation systems. So it's usually very long form, it's structured, it's sort of formal English. On the other hand, Twitter data on the bottom here is an example. It's limited to 140 characters in size, and usually there's a lot of slang, so and colloquial language. So I guess in machine learning terms, there's obviously a distribution mismatch here between these two bodies of text. And because of that, we noticed that the performance of these embeddings might not be as good as they could be if we close this distribution gap. So here is our solution. We add a fine-tuning phase to the training of these transformer models, where we take our data set of tweets and then we train or fine-tune the transformers on the data set of tweets in an unsupervised way. So again, we're using the MLM, masked language modeling loss. And then after this fine-tuning, it's the story is the same as always. So we take a tweet, we pass it through the transformer model, we get a fixed size embedding, and then this fixed size embedding goes into the multi-layer perceptron or fully connected network to predict each of the 4 engagements. Here's some details on the training of these language models. So maybe at first I would tend your attention to the right here. So what we're looking at is the perplexity plot, or basically you can think of this as the unsupervised learning performance. So lower is better. And the curves for both of our models, multilingual BERT and XOM Roberta, are shown. So that's blue and red respectively. And I think what I want to draw your attention to here is the fact that the perplexity is quite high at the beginning of training. And that sort of means that these embeddings are not as good as they can be, and that there's, this is what we're saying about the distribution misalignments between the pre-training data and the tweet data. And then over time, as you train them, you fine-tune these models, the perplexity goes down, and presumably this corresponds with better embedding quality. Now on the left, you see some details of our training. So we initialized the transformer models from their pre-training stage on Common Crawl and Wikipedia. We fine-tuned for 2 epochs and 8 NVIDIA GPUs. And then we found a triangle learning rate schedule to be very important to use. So this means in the first 4,000 steps, gradient steps, we linearly ramp up the learning rates. And then for the rest of training, we linearly decay the learning rates. And then maybe the most important detail here is, well, where do we get the embeddings? So we chose to use the last layers of the transformer to extract the embeddings. And in particular, what we did is we took the mean embedding from the last layer. Now, I think there's a lot of thought around what to do here in the NLP community. I think some people think that it's better to take from the middle of the transformer, or it's better to take sort of the max instead of the mean over embeddings. And these are not things we investigated very thoroughly. So there might actually be more room to improve here if you sort of have a better process for extracting the embeddings. And maybe just one more thing I'll mention. We did try training the transformers from scratch. So we tried training our own tokenizer, and then we tried training, we tried initializing the weights from random, and then we tried training them on the tweet datasets. We it was a little bit difficult to get this to work. So I don't want to kind of say that it won't work, but it was much easier for us to initialize from pre-trained weights and then fine tune from there. Okay, so now we have our tabular features and we have our deep learning tweet embeddings. So the final step here is to combine them in a MLP model. For those who've tried to, so the goal here is we want to basically match the XGBoost performance and then succeed it using our MLP model. And for those who've tried to match the performance of XGBoost using deep learning on a tabular data set, I think you all know that this is actually non-trivial. So XGBoost is very performant and it's hard to match its performance. So in order to achieve that, we had to use a few tricks. And the most important trick here is the Yeo-Johnson transform. So if you look at the picture here, this is basically what's going on. So the red plot, imagine this red plot is the distribution of one of your tabular features. And the idea of the Yeo-Johnson transform is to apply a monotonic nonlinear transform to kind of massage this distribution into what you see here in the blue. The intuition for Yeo-Johnson transform is, I think in some sense, very similar to batch norm, because neural networks, they work well when the inputs looks unit Gaussian. And for batch norm, you're trying to make the hidden layers outputs unit Gaussian looking, roughly speaking. And for the Yeo-Johnson transform, what you're trying to do is you're trying to make the inputs of the neural network unit normal looking. So we took each of our tabular features, we passed them through the Yeo-Johnson transform, and then we pass that into the MLP or fully connected neural network. So here's a look at how our MLP model does without the tweet embeddings. So here we're just trying to show that it can kind of almost match the performance of XGBoost. So it's pretty close, but it is a little bit behind on the comment engagement. Now, when we add the tweet embeddings into the model greatly surpasses the performance of XGBoost. And now we can ensemble these two models and into our linear ensemble, and they will do sort of even better. Okay, so I've talked at a high level the three sort of pieces in our deep learning model. Now I'll spend the rest of the time going into a little bit of detail of what our of this model. So here is the sort of the full diagram of our model, and I will be highlighting each section in turn. So here, the first part is just a summary. So we extract some tabular features using XGBoost. We train a language model using in an unsupervised way on the tweet data. We fine tune it, and then we pass these and we extract embeddings for each tweet in the data sets. We pass both tabular features and tweet embeddings into the MLP. And then this part is the part I haven't touched on yet, so in addition to this multi-layer perceptron, we also have a attention module here. And the intuition for this is the following. So what we're trying to do here is we're trying to build up a profile of each of the users in the data set. In order to build up a profile of the users, what we do is we take all the tweets this user has engaged with in the past, and we treat that as sort of a memory bank. And the idea here is you take the current tweet that you want to make a prediction on, i.e. the target tweets, and you're going to try to use that as a sort of a query to figure out which previous tweet in this memory bank is the most relevant to look at for the current prediction. And that's what you're seeing here on the right. So basically what we're doing is we're taking all these previous tweets that a user has indeed engaged with. We pass them through the transformer model to get these list of embeddings. And then we encode the embeddings into a key value query attention system. So this is quite a vanilla sort of attention system. And then using our attention module, the tweet embedding is able to retrieve the embedding from the past that's the most relevant, and that's encoded as a history embedding. Finally, we take the history embedding and we take the target tweets embedding, and then we take the tabular features, we pass all three into the multi-layer perceptron. Here's some details on what this history embeddings look like. So for a given user, for each of the 4 engagements, we take up to 4 tweets that he or she has engaged with in the past. up to 10 tweets that each of for each of these 4 engagements. And the target tweet is able to attend on any of these and retrieve the most relevant one. So here's basically a high-level picture of what's going on here. And taken together, this is our final model with tabular features, with deep language model, with attention. And this is the performance of our model using this attention module. I will say it's not the biggest improvement over not using it, but this model was quite sort of resource intensive to train, and we do believe we can kind of squeeze more juice out of it. We had sort of a larger memory bank, and if we use other things like previous tweets this creator has created and things like that. Okay, so the last thing I want to show you is I want to discuss a little bit about the benefits of explainability in a deep language model. So here's what explainability usually looks like for GBMs. So you have some sorted rank list of the top features that are the most important. You have the feature name, and then you have some measure and performance, whether it's some splitting metric or the SHAP values or something like that. But what does an importance value of 6,192 really mean? In fact, what does it mean for the user ID to be one of the top features? Here's a look at the attention weights of our transformer model. So what I'm showing here in green are the words in the sentence that have the highest attention weights. And for context, this is a tweet that a user did indeed engage with. So now we can sort of ask the explainability question, why do we think this user engaged with this tweet? So it could be the fact that there's a podcast that is linked in this tweet, and maybe the user followed through the podcast and they liked it, and that's why they engage with this tweet. Maybe there's a sort of call to action word here in the verb subscribe. Or maybe the user likes Broadway or theater. Or maybe the phrase, my funniest friend, is very catchy. So these are all insights that a deep language model can provide to your predictions that a gradient boosted system cannot. Here's another explainability example. So what's going on here is the top tweet, the target tweet is the one we're interested in, is the one we want to predict whether someone engaged with or not. For context, again, this is a tweet that a user did indeed engage with. On the bottom is this memory bank I was talking about. So here we're looking at the attention weights in the sort of the attention module in our network. And the bottom tweets are the sort of the reference tweets, the previous tweets that this user has engaged with. And what I'm showing in the square brackets are the attention weights of our attention module. So the take-home message here, so again, we can kind of ask the question, why did this user engage with this tweet at the top here? And if you look at the reference tweets, especially the ones highlighted in green, those have the highest attention weights, the pattern here seems to be this user engages with coronavirus tweets. And furthermore, I want to draw your attention to the tweets highlighted in yellow. So these tweets are actually written in Russian, and they're sort of about the sort of international finances, and they're not so much related to the coronavirus tweets. But the thing I want to sort of illustrate here, it's these deep language models can sort of reason over so many different languages at the same time, right? So basically, this data set had over 50 different languages, which is amazing. Doesn't matter which language you have the tweet, you pass it through the transformer model, you get a fixed size embedding out. So the transformer model is able to jointly reason over all these 50 different languages. Now imagine if you were trying to—
Sorry, Kevin, you have 1 minute to wrap up.
Oh, we're just wrapping up here, so I think we're good. Yeah, so imagine if you were doing feature engineering over all 50 languages, you would have to basically understand all these 50 languages, right? So and that would be quite challenging. So as promised, I'm just wrapping up here. So thank you very much to the organizers. Thank you so much for everybody for listening in. We at RecSys had a fantastic time working on this data set this year. It was very challenging, very insightful. We learned a lot. And I just want to put in a quick plug. We at RecSys, we're still hiring despite of COVID. If you want to join a team of very highly motivated, energetic, talented individuals, or if you kind of just like how the Toronto skyline looks, drop me an email or reply to one of the job postings at the conference. Thanks again, everyone, for your time.
Thank you so much, Kevin. Very, very insightful presentation. So please, could you remove the slides? Okay, thank you so much. So first of all, I would like to defend a bit the challenge. So you mentioned this data leakage that happens at a certain point in the middle of the challenge. So as Twitter mentioned in the introduction, this was not, a proper leakage, given that all the data provided were just basically a dump on a public data set, which is Twitter. So on our side, we try to do the best in order to prevent it. So as you participants know, so the only thing we could do was basically to check all the submission at the best of our possibilities. So this will probably follow up in the panel. So at the last session, if you want to also compare with NVIDIA and Twitter, everyone will be there. So just to say one word on it. So let me ask you a question. So this is again a very interesting work, and an impressive amount of different technology used. So in the paper you mentioned that the final classification model is basically exploiting multitask classification paradigm. So you are basically predicting all four classes at once. I was wondering if you tried instead to split the classification models. So instead of one multitask using 4 binary classifiers, and if you notice, I was expecting that the multi-class with the shared weight would be better. So did you try it, and you can provide some insight?
Yeah, that's a great question. So I think just to clarify, our deep learning model, what we did was we used a sigmoid loss on each of the 4 engagements. And I think this is the most intuitive thing to do, right? Because so for each sort of data sample, there can be more than one positive engagement. So you don't want the engagements to be competing with each other. And to that note, most of the layers in our deep network were shared between the 4 engagements. So it's only up until the very last sort of linear layer where it splits off and you get 4 heads with 4 different sigmoid losses.
Okay, clear. And one very quick and last question on my side. So in the paper, you provide also a very interesting ablation study. So can you comment a bit on it, especially which of these components contributes the best to your prediction? And what do you think it was the most important ingredient in this complex receipt?
Right. So I think the story here is kind of like stacking on layers and complexity, right? So the foundation is we first had to get the XGBoost to work. And then we had to get the deep learning model to match or get close to the performance of the XGBoost. And as I sort of mentioned in the presentation, this put us around sort of the 3rd or 4th place ballpark range. And once we got that working, we had to get the deep language model's embeddings to work. And then once we could incorporate this in with the rest of the model, that kind of put us very close to our final sort of performance. And then the final thing we added on is the attention module. And that got us, I think, about 0.3 AUCPR or something like that, 0.3 to 0.5. And the very, very final step is to do the sort of the linear ensembling. And this got us another like 0.5 or maybe closer to 0.8 AUCPR.
Okay, good. So thanks for answering my question. And
we have the last question in the Q&A panel.
Okay. Okay, someone is asking, can you give some more detail about how do you pass the user history to BERT?
Sorry, I didn't catch the second last word. How to best use the...
How you pass the user history to BERT, to the language model.
Oh, how to use the history for the BERT model, or?
Yes, so some more detail about how you do it. So to pass this user history to the BERT model.
Ah, okay. So when we say user history, we mean sort of the array or list of previous tweets this user has engaged with, and this is what kind of makes up the user history. So we have this sort of basic list of strings, and then we have the BERT model, and then we basically pass the sort of list of previous tweets through the transformer model, and we get a list of embeddings. And these embeddings are what the attention sort of network is attending over.
Okay, this is very clear. Thank you. So we are a bit late, so let's invite immediately Carlos Miguel Patiño. He will present his work leveraging user embeddings and text to improve CTR prediction with deep recommender system. So please, Carlos, come on stage.
Okay, thank you, Gabriele. Can you hear me okay?
Perfectly. Please share your screen.
Okay. Okay. You see my screen, full screen?
Please, you can start.
Okay. And thank you, Gabriele, for the introduction. I'm Carlos Miguel Patiño, and I'm going to talk to you about how we at Factor leverage user embeddings and text with the recommender systems for the RecSys 20 challenge. First, a quick review about the challenge. The objective was to predict whether a user will engage with a tweet with 4 possible types of interaction: retweet, reply, retweet with comment, and like. And as the previous team mentioned, a user could interact with a tweet in multiple ways. For example, a user could like and retweet the same tweet. The data set we had for the challenge was a huge data set. We had around 160 million tweets with possible engagement sampled over 1 week. And those 160 million tweets had around 30 million associated users. So a user could be either a possible engager, that means the user that is seeing the tweet, and also the user that wrote the tweet, the author of the tweet. And an important feature of the dataset was that it only contained public information that was available on Twitter. So for example, if a user published a tweet on Twitter and later deleted the tweet, that tweet was also deleted from the dataset we had available for the challenge. And as everyone has mentioned, the 2 metrics to optimize during the challenge were the relative cross entropy and the area under the precision recall curve. As you can see, the dataset, the challenge had 2 phases: a huge dataset that required processing, and also a modeling phase to predict engagement. We at Factor specialize in building ML teams and data science teams for our clients. So for this challenge, we had a mixture of data engineers, machine learning engineers, and data scientists, all part of Factor. And we were distributed between Medellin, Colombia, and Palo Alto, California during the challenge. So let's now dive into what we did for our solution, starting with the data processing phase. As I mentioned, there were around 30 million users in the dataset, and we wanted to build user representations for these users. The thing is, 30 million user embeddings are a lot of embeddings for a model to learn during training. So we instead followed a user bucket approach. The approach was the following: if a user had more than 71 appearances in the dataset, what we did was assign an entire bucket for that user. But if a user had fewer than 71 appearances, what we did was follow a clustering approach. So what we did was using user features such as number of followers, number of users that user followed, whether the account was verified. We used k-mean clustering to build 60 user clusters. And then each cluster, we split it into user buckets. Why we did that? That way we could guarantee that users that ended in a single bucket were similar users, and then we built an embedding for the entire bucket. What were the benefits of this approach? Instead of making the model learn around 30 million embeddings, it had to learn instead around 200,000 embeddings, and that saved a huge amount of memory that the model used during training. Also, for users that had few data, we leveraged on similar users to learn better quality embedding. So we had a better representations for users that didn't appear much in the dataset. And also, if there was enough data for a good quality embedding for the user, we did have a single user embedding for that particular user, because since the user was the only one present in that bucket, we had only data about that user in that embedding. Now, we had user representations through embeddings, but we also wanted to use information available on the text. And this information was provided for the challenge in text tokens, in BERT text tokens. So what we did was first encode these text tokens using a pre-trained BERT model, and then reduce the dimensionality of these encodings using PCA. We use these text encodings as raw features we pass through to the model, because these text encodings represented the semantic meaning of the tweet. So that provided useful information for the model. But also what we did was create clusters for these text encodings using a k-means algorithm. What was the advantage of clustering these text encodings? Since the text representations contain the semantic meaning, text encodings that end up in a specific cluster means that they have a similar semantic meaning and can be thought as topics, as the topic of the tweet. So what we did was create 150 clusters using the k-means algorithm, and assign a topic to a tweet. And also, since we had the topic of the tweet, we could assign the topics that were most seen by the specific users in the dataset. So what we did specifically was take the 5 topics most seen by a user and calculate how many times that user saw that topic during the week that was sampled in the dataset. What were the benefits of this approach? First, training a BERT model is very expensive computationally, so we only fed the text tokens once in the data processing phase, and we didn't train the BERT model. So we saved a lot of training resources. And also, although we didn't train a BERT model, we did have text representations from a powerful language model that is BERT. And also, through the topic features, we created features that encode which topics were most seen by a user and how many times the user saw that kind of topic. So we, on the one hand, through the text encodings, we let the model know the semantic meaning of the text. And also through the topics, we let the model know which types of information was most relevant for a specific user. And to finish up the data processing phase, we wanted to build a small validation set to optimize evaluation time, because the data set was huge and training time was very valuable, but we still wanted to constantly evaluate our model. So we wanted to build a small validation set, but as a validation set should do, it should indicate the performance we would have on the submission set, on the set we had to upload to the competition. So what we did was create a small validation set of around 500,000 samples, that is less than 1% of the training set. And to avoid data leakage through time dependence, we chose the last 16 hours present in the data set. Remember, we had around 1 week of data, so we chose the last 16 hours of that data. And we simulated the ratio between cold start and warm start users we observed on the submission set. So the validation set had the same ratio of cold start and warm start users that we had on the submission set. Here's a diagram with a detail of our data split. Users 4 and 5 were the types of user we observed on the submission set. User 4, the warm start user, and user 5, the cold start user. So to simulate those types of users, what we did was first to create a type of user as we show on user 1. This is the warm start user. The model sees that user during training, and it has to predict engagement during validation. User 2 is how we simulated the cold start user. What we did was delete any appearances that user had, so the model didn't see that user during training. And it had to predict possible engagement during validation. User 3 was our way of showing the model that it would encounter cold start users during training. So what we did was remove historic features of that user, particularly the topic features. So what we did, if a user did have associated favorite topics, what we did was impute those favorite topics with random topics and set the count of those topics to 0. So the model knew how to handle these types of cold start users. And also, one thing we wanted to show with the user 4 is that we didn't include any user that was in the submission set. We didn't validate with that user. With which purpose? The purpose was to include all the appearances we had for users on the submission set, so the model could learn as much as possible during training about these models about these users, that were in the submission set, to enrich the user embeddings that we talked about at the beginning of the talk. So that's it about the data processing phase. Now about the engagement model we built for the challenge. First, we didn't want to reinvent the wheel in terms of click-through rate prediction architectures. So we did a literature review, and we found that the most successful models in the literature were the factorization machine, that we took a slightly modified version of the factorization machine, the AutoInt model that used the transformers to calculate interactions between features, and the DeepFM model that used fully connected layers to calculate these interactions. Also, we knew from the organizers of the competition that conversation on Twitter shifted and changed really fast. So we wanted to make our model robust to those kinds of changes. And we used batch normalization between the layers we had in our model, because this batch normalization makes the model robust to data shifts. So that help us make our model robust to changes in the conversation on Twitter. And also, since the user embeddings were central to our approach, we used skip connections. So we could make our model deeper without hurting the learning the model could do about these embeddings. Here's a diagram of our model. As you can see, the engager embeddings and the author embeddings are connected directly through a connection to the interaction components, and also to encoders that we defined for each type of entity we had in the problem: the engager, the text, the tweet, and the author. Each of these encoders received features related to each of these entities we had in the problem. And here in the diagram, we place the transformer that was based on the AutoInt architecture, the deep learning component that was based on the deep branch of the DeepFM architecture, and the custom FM that was based on the factorization machine. Why do we call it custom? Because typically the factorization machine has a scalar output. But since the transformer and the deep learning, we could make vector outputs to fit 2 additional layers on the output layers, we modified the factorization machine so we could have a vector output. And those 3 interaction components had a vector output that were fed to additional layers in the output layers. Here we show in the output layers, we have a component for the retweet and retweet with comment engagements. Why did we define a single component for those 2 interactions? We observed that they were very correlated in the data set, and also that they had few positive data. So what we did was use weight sharing for these 2 types of engagement to learn a representation and then output that representation to actually predict whether there was going to be an engagement between the possible engager and the tweet. Here were some ablation studies we did for the components I just mentioned to determine which one was more relevant for this particular challenge and according to our architecture. And the component that we tested and was most relevant was batch normalization. So our hypothesis is that the conversation on Twitter actually changes very fast, and making the model robust to those changes in the conversation on Twitter was very important to achieve a good performance during the challenge. And also the topics were important to let the model know which types of text were relevant to the user, and signal the model which type of topics would possibly trigger an engagement. And on the other side of the coin, we determined that the transformers as an interaction component weren't as relevant for this architecture we use for the challenge. They were relevant in terms of encoding the text, but not as an interaction component to calculate interactions between the features we use for the challenge. Because as we show here in our application studies, it actually made the model overfit to the training data and do poorly on the validation set. So just to finish up the talk, we, as you can see, we took design decisions during the challenge to optimize our computational resources while maximizing the two metrics we had for the challenge. Specifically, we used user buckets to reduce the number of embeddings the model had to learn during training, and also learning better quality embeddings for users with few data in the dataset. Also, we used topics and text representations, but without including BERT in our model to skip training BERT in the training process. And also through our application studies, we showed that the modifications and additions we made to the architecture we found in the literature did improve the model's performance. And here's our contact information if you want to ask us online about this work or about what we do at Factored, and I'm happy to answer any questions you may have now. Thank you.
Thank you so much, Carlos. So I will give you the question we have from the audience. So how did you handle the new categories in the validation set that are not in the training set?
When you mean categories, do you mean topics or?
Yeah, I think they will mention the topics that you extract from the clustering approach.
Okay,
I guess.
Yeah. We didn't have to handle the new categories. What we did was just for the validation set, we calculated the text representation and assigned that representation to one of the existing clusters. So we didn't create new categories for the validation, just assign that particular tweet to the existing clusters we had on that we generated through the training set.
Okay, clear. Very quick question by myself. So you mentioned in the paper that you use 150 clusters. So I was wondering how you optimize with this number, and if you consider to use like some automatic methods to find the optimal number in this dataset.
Yes, all the cluster the number of clusters in both in both clusterings we optimized using a simple elbow method. We found that it's a simple method, but it was an effective one, so we didn't explore further in that avenue.
Okay, thank you so much. So thanks Carlos once again. And so now it's the turn of our last contribution for this session. So the presenter will be Luca Conterio from Politecnico di Milano, and work presenting is the multi-objective blended ensemble for highly unbalanced sequence-aware tweet engagement prediction. So please, Luca, okay, you're ready? Or...
Okay, do you see the presentation?
Yes, please. You can start.
Okay. So good evening, everyone. I'm Luca Conterio, and I will present the Banana Never Alone team paper, which deals with a multi-objective ensemble model for imbalanced data engagement prediction. We are 5 computer science and engineering students from Politecnico di Milano University, supported by 2 PhD candidates and Professor Cremonesi. In the following, we are going to talk about the RecSys Challenge 2020, in which the task was to predict the probability that a user will engage with a tweet, given a big data set of around 80 gigabytes of tweets sampled during 2 weeks. The engagements could be of 4 different types, like retweet, reply, and retweet with comment. And the last 2 in particular were highly unbalanced. In fact, the dataset contained only the 2.5% of replies and the 0.7% of retweets with comment. The ranking is then computed combining the 2 metrics that are the relative cross entropy and the precision recall area under curve. Our solution relies on some features that we built starting from the original dataset and on 2 different types of models, the gradient boosting for decision trees and neural networks, which are then combined in an ensemble model. Since the challenge dataset was split in 90% for training and 10% for validation, we maintain this ratio also in our local split. And moreover, we tried to maintain the called users percentage consistent in the validation data by moving some users and their engagements from the training set to the validation set. And this resulted in a split of around the 88% for training and the 12% for validation. Validation data timestamps are also shifted 1 week in the future in order to reproduce the challenge dataset time distribution. A great part of our work deals with feature engineering. In fact, we built around 300 features in total, but we used only half of them for the final solution, since some of them were harmful for our models. The main ones regard the user behavior, the user affinity, and the languages of the tweets. By inspecting the dataset, we noticed that different users had different behaviors. In fact, for example, in the top plot of this slide, we can see that the behavior of the users that often put likes. We have on the horizontal axis the users sorted by the number of likes given, and on the vertical axis the number of engagements in total. For example, we use the blue for the like class and the orange for the retweet. And we can see that users that usually put likes tend not to perform other types of engagements. In the bottom chart, instead, we did the same, but for the retweet class. And we can see that users that usually retweet are more prone also to put likes, for example. In order to encode these behaviors, we built the number of active and passive engagements features in which that are computed for each engagement class and are associated with a specific user. The number of active engagements it counts the number of engagements a user had, counts the number of engagements in which the user appears as an engager, trying to model how likely is the user to interact with the tweets. The number of passive engagements instead counts the number of engagements a user received, modeling his popularity. Focusing on the languages, we show here in the slide 3 sample languages, and we notice that different languages have different dynamics. The plot shows the probability that if a user interacted with a language, he will only interact with tweets in that language. And for example, we can see that around the 70% of users that interacted using Japanese will only interact with Japanese tweets. Instead, users that use Korean are more prone to use also other languages. In order to catch these dynamics, we built the number of engagements with the language, which counts the number of engagements that a user had with tweets of the same language of the current one, trying to model the languages a user speaks and those the user may understand and engage with higher probability in the future. Finally, we also built a social graph between users in which edges have a weight which is equal to the number of interactions between those users. And from this graph, we computed a user similarity feature. But for computational reasons, we only use the 1-op and 2-op similarities. The features that I just showed were computed in two different ways. In the first method that we call the timestamp aware, features are computed using all the engagements that occurred previously, according to the tweet creation timestamp. In this way, the same user is associated with different feature values as time progresses, modeling a sequential engagements pattern. In the second method, instead, that we call the cumulative, the training data is split in 20 folds, and for each fold, the features are computed using the data contained in the remaining 19 folds. And this method showed to improve the model's robustness, since it is not sensitive to the sequential patterns and uses the whole user history. Speaking about the models, we used the gradient boosting models for decision trees, which are well known to perform well in this type of challenges. And we used two implementations that are XGBoost, which allowed us to build models using sparse datasets, and LightGBM, which had faster training time compared to XGBoost. As I said previously, we also used neural networks. In fact, with the gradient boosting models, we were not able to exploit the textual informations contained in the tweet. We fine-tuned a pre-trained Distilbert model, which is a lighter and faster version of the popular BERT transformer. We added two dense layers on top of the pre-trained model, and each of them is followed by dropout, since such a big model is prone to overfit. The first dense layer instead, in addition to the text embeddings, also takes as input a set of other features that are normalized using a Yeo-Johnson transformation in order to ensure that they are normally distributed. The fine-tuning process was necessary for the model to understand some semantics of the hashtags, mentions, and links that are contained in the text of the tweets. Our first solution was a single network having 4 output neurons, which of course had benefits in terms of computation time with respect to 4 different networks. But we noticed that we had better results using a mixed strategy, in which we had one network with the 2 sigmoid output neurons for the like and retweet classes, trying to catch the correlations between these 2 classes, and 2 separate networks for the reply and the retweet with comment classes. Moreover, we took 2 small subsamples of the training data, and we trained 2 instances of each of these networks, because training them on the entire dataset was infeasible for us for computational complexity reasons. As I said previously, we built an ensemble model, which is composed of some base models that trained on the training data produce predictions both for the validation and the test sets. These predictions are then used as new features for respectively the validation and the test data. The ensemble model then that is implemented using LightGBM is trained on the validation data and produces the predictions for the final test set. In the final ensemble model for the retweet reply and the retweeted comment classes, we decided to use the predictions given by the predictions for all the classes, except those for the like class given by the gradient boosting models, since they lead to worse performance. For the same reason, in the ensemble model for the like class, we decided not to use any prediction inferred using the gradient boosting models, but only the neural network ones, along with the features that I previously described. During the hyperparameter tuning of the gradient boosting models, we noticed that the high class unbalance for the reply and retweet with comment classes intended to steer the model to simply predict an engagement probability of 0. Also, an algorithm providing a constant prediction was able to achieve a very high PRAUC in these two classes, higher than the 0.5, but a very low RCE. In order to penalize this scenario in which models could achieve a high PRAUC but no discriminative power, we defined a custom objective function that combines the two challenge metrics. In particular, when the RCE is negative, it is divided by the PRAUC, which results in a worse value for the objective function. For what concerns the retweet with comment class, the tuning process identified two optimal solutions for the ensemble model, one with a higher PRAUC and one with a higher RCE, that we called respectively comment P and comment R. The main difference between these two models is that even if they have more or less the same mean, a higher PRAUC is associated with a greatly reduced variance, as it is shown in the figure of this slide. I will now show some results of the models that we used. This table shows the best XGBoost and LightGBM models, both for PRAUC and RCE, on our local validation set. And during our experimental evaluation, we noticed that LightGBM scored better results than XGBoost, reaching, for example, an RCE of 4 points higher in the light class. For what concerns neural networks, we can see that the mixed strategy using the two network instances S1 and S2 performs better than the 4 labels version. For this reason, in the ensemble model, we decided to use the predictions given by these two instances. And even if they perform slightly worse than the gradient boosting models, they used different information and so led to an improvement of the ensemble performance. Finally, the ensemble. This table shows both the performance of the ensemble for the local validation and for the leaderboard. And we can see that comment P gains a lot in PRAUC with respect to comment R, while not losing so much RCE. The two submissions that we made included the same predictions for like, reply, and the retweet classes, while they differed in the retweet with comment ones. In fact, one solution included the predictions given by comment P and the other one those given by comment R. We missed the results for the final leaderboard for comment P for comment R, since comment P performed better and reached the 4th place in the leaderboard. And this is all. Thank you for your attention. Also, I would like to thank the organizers and the Twitter team for this challenge. Thank you.
Thank you so much, Luca. Very interesting presentation also on your side. So first curiosity on my side, so is that in your case, with respect to layer 6 solution, the single, let's say, binary classification of the single engagement class worked better than the multitask predictor. So I was wondering if the architecture of the two networks were the same and how you optimize it.
Yes, well, actually we did not use a single different network for each label, but the like and retweet classes were trained together. Mm-hmm. Because we noticed some correlation among these two classes. And yes, so we have 3 networks in total, one for like and retweet, one for reply, and one for the comments. And yes, they had the same structure. Okay, so also the multi-class had the same structure of this one. Okay. And we tuned them with a simple grid search.
Okay. Then in the paper, you mentioned that you extract around 300 features and then you decide to discard many of them. So how you decide to do this? So how you perform this feature selection?
Well, some of them were harmful, as I said, because due to the sequential time distribution of the tweets, some of them were built in a way that leaked some information that was contained in the validation set. And so we noticed that we had a very good performance locally, but then in the leaderboard we had a very big discrepancy. And so we discarded some of them due to this overfitting problem.
Okay, so it was some post-processing, let's say, on the results that you noticed. And okay, we have also one question from the audience. So at the validation result slide, the neural network results are not as good as light GBM. Could you please explain it deeper?
Yeah, it was slightly worse than the gradient boosting models, because we used, for example, we used less data. We used only for each training of each network, we used around 2 million samples only, because of the training time that was needed for the networks. And so yes, they performed worse. But as I said, they improved the final ensemble model because they were the only models that used the textual information contained in the tweets. That was not used by XGBoost and LightGBM.
Okay. One final question on my side. Your architecture, as far as I understood, let's say optimize the ensemble given the prediction of some single models like the free neural network that you describe. So did you consider to experiment instead with an end-to-end training architecture?
Can you repeat, please?
I mean, instead of having some prediction from some single model to directly optimize to the ensemble prediction. So having the train on the final prediction on the ensemble.
Okay, no, we first tried training an ensemble using the predictions of the base models, as we call them.
Mm-hmm.
But we noticed that we achieve better performance, also including the same features on which the neural networks XGBoost and LightGBM were trained. So this was the rationale.
Okay, thank you for your answers.
Thank you.
So let me conclude this session. So I want to thank once more all the interesting presentation and the presenters that we had in this session. So I also want to remind that in the next session, we will have some interesting talks. So first of all, the first place by NVIDIA. So their work will be presented there. Also a position paper by Dietmar Janak and the winners of the challenge, discussing why deep learning is not consistently winning the RecSys challenges in the last years. And finally, the panel where these Janak and the two winners of the challenge will discuss together with Twitter the take-home message of this year's challenge. So I think it is all for this challenge. So see you in an hour for the third session. Thank you, everyone.
Coming out for any reason. Here we go.
Hello, welcome. In this workshop, Team NVIDIA Rapids will present their first place RecSys Challenge 2020 solution. Enjoy! My name is Chris Diott. I am one member of the NVIDIA Rapids team. Our team consists of 7 Kaggle Grandmasters of NVIDIA, KGMON, and 3 NVIDIA Recommendation System experts. The 10 team members are listed here. Today we will present our solution. The full code and a PDF written paper of our solution can be found at the GitHub repository link shown here. We would like to thank the sponsor, Twitter, and the 5 organizers listed here for hosting an exciting recommender system competition. The competition lasted from March 1st through June 15th. Our team was very excited on the morning of June 20th leaderboard. Our model predicted 4 targets, and the combined total relative cross entropy RCE was 132.5. Second place had total RCE 92.9, and third place had 90.1. This year's competition was predicting user behavior. When a user sees a tweet, we needed to predict whether the user liked the tweet, retweeted the tweet, retweeted with comment, and/or replied to the tweet. Full details about the competition can be found at the URL shown here. The data we were given to build our models had 121 million rows and 24 columns. Each row represented one interaction between a specific tweet and specific user. We needed to use the 20 columns of features to predict the 4 behavior targets. A third of the features were about the tweet. A third of the features were about the author of the tweet, hereafter referred to as user A. And a third of the features referred to the audience of the tweet, hereafter referred to as user B. To name a few examples, you can see there's a column called language. This indicates the language that the tweet was written in. There was another column called a follower count. This refers to how many followers the author user had. Without further ado, let us show you our first place winning solution. Drum roll, dun 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 dun! XGBoost. Our winning model was an ensemble of 3 boosted tree models. The code for our XGBoost models are displayed here on the right, and the performance of each of the 3 models is displayed in the table on the left. We can see that our most accurate model, model number 3, achieved an overall leaderboard RCE of 126.9 by itself. That single model could win the competition by itself, but when we ensemble that model with the other 2 boosted tree models, it had an overall leaderboard score of 132.5. Looking at model 3, we see that column, we see that the reply had a leaderboard score of RCE 23.3 with a local validation of 24.6. It had a retweet 36.1. It had a comment RCE 15.2, and it had a like RCE of 52.3. We tried many types of models besides boosted trees. We tried deep learning neural networks. We tried matrix factorization like alternating least squared to learn the embeddings. We tried BERT transformers, FTLR, follow the regularized leader. But all in all, we observed that most models performed the same. The secret to our success wasn't the model per se, but engineering new features. So the original dataset only gave us 20 columns, but we made hundreds of new columns to help our model learn the information. This was made possible by using Rapids, an open source library which does data frame manipulations on the GPU. We could create a new feature and then validate it in a model to see if it increased our model accuracy in under a minute. This allowed us to try hundreds and hundreds of new features and find all the features that increase our model accuracy the most. The secret to our success was engineering features extremely quickly. In the bar plot here, the bar on the right shows us that when using Rapids with 4 GPUs, we could engineer 115 features, train 4 models, and predict 4 validation sets in 138 seconds. If we attempted this procedure on CPU using optimized code on 20 cores, it would take 3,570 seconds. That's a 25 times speedup. This means in the same amount of time, we can explore 25 times more features to find those features which will give us the most accurate model. By looking at the bar plot on the left, we notice that when testing new features, the majority of the time is spent in creating those features because it's computationally intensive to transform one column into a new column. You can see by the colors that the 3 most popular types of feature engineering we did were target encoding in the blue, count encoding in red, and lag features in yellow. The time to train here, which is shown in the green, is only about 1/4 of the whole experimentation pipeline. We will discuss more about this speedup throughout our talk. The training data set was 1 week in time, and the unseen test data was 1 week in the future. To mimic this, we validated locally by training on the first 5 days of the week and predicting the last 2 days of the week. We will now show you some of our new creative features and how we engineered them. Here is a list of our 13 most useful features for predicting the target light for our most accurate model, which earlier we called model number 3. We can see here that the most helpful features have a prefix of TE, which means target encoding. So target encoding features were our most powerful. Let's look at an example. If you look at the 6th one down, it's called TE_ACount_combined_tweet type_language_like. What that means is we combined 3 columns and then target encoded it with the column like. The 3 columns that were combined were ACount combined, which that in of itself was a new created column. Second was the column tweet type, which was one of the originally given columns, and language, which was originally given column. Looking at another example, 3 up from the bottom, we see T_links_media type, media_tweet type _language_like. This means that we target encoded the 4 combined columns, links, media, tweet type, language, and we target encoded with the target like. In layman's terms, what this means is that certain combinations of tweet language combined with the type of tweet it was, combined with the type of media is present, whether there was pictures in the tweet, etc., combined with links that were present in the tweet. So certain combinations of those things indicated that a person was going to like the tweet more often than not. In the next slides, we'll explore this more in detail. Since target encoding is our most powerful feature engineering technique, I wanted to explain it in some detail. So here's an example with fictitious data. Imagine we were given 3 columns, a column of username, a column of language, and a column of target. And here you see there's 2 users, Allison and Brian, and 2 languages, English and Spanish. So to target encode the column user, what that means is you find a specific user, such as Allison, and then you look at the ratio of which targets are 1. And if we do this, we see that when given user Allison, 50% of targets are 1. You then create a new column called target encode _user, where in the same row as Allison, you put the number 0.5. That's the 50%. Likewise, if we find the user Brian and we look at which proportion of targets are 1, once again, we see it's 50%. So it's, okay, now let's target encode language. So you look at all the rows that have language English, and then the proportion of targets that are 1 are 50%. You add 50%. We do that for Spanish. So I purposely made this example to illustrate something. When you target encode user and you target encode language, the new column didn't tell us much. It just says that there's a 50% chance for everything. So that wasn't very helpful. Now let's look at what happens when you do a multi-column target encoding. So now what we do is we will target encode the column user and language together. That means we will now consider all the rows that have both Allison and English in them. So there are 3 such rows, and then amongst those rows, 66% or 2/3 of the targets are 1. So therefore, in every row that has Allison and English, we will add a value of 0.66 in our new column, target encode user underscore language. So we will do this for all combinations of user and language. So you can see target encoding is like a conditional probability. In the top right, the formula says that target encoding of user or language is the probability that target equals 1 given we have a specific user and a specific language. I use the word probability, but what we really do is we just compute the proportion of targets that are 1 from the training data. Once you compute these target encoded values from the training data, we then take those values and we add them to the validation data and the test data. Because remember, we don't know the targets in the validation data and test data. And you can see that in the example here. The Allison-English combination we computed earlier, the first row in the validation data and test data we set to 0.66. So that is how you do multi-column target encoding. Target encoding is performed by the data frame operation group by aggregate mean, as shown in the second line of code here and discussed on the previous slide. However, if you use this simple target encoding, it will not predict well on unseen data. We additionally need to add the technique of smoothing and k-fold. Let's look at the 2 plots here. They represent target encoding the column B user ID. The x-axis is the value that shows up in the new target encoded column, and the y-axis is how frequently that value shows up. Notice in the plot on the left without smoothing, the value of 0 and 1 show up often. How is this possible? This occurs when you have a user that only appears very infrequently. Imagine there's a user called Tom, and he appears only once in the training data set, and the one time he appears, let's say that he likes the tweet. Therefore, you would compute 100% of the time Tom likes the tweet. So then, when you predict unseen data and you see Tom, you'd predict 100% of the time. However, that one observation is not enough to be confident. So in that situation, it would be better to just compute the overall average of likes, which is 43%. And then in the case of Tom, just predict that he likes at 43%. So that's what smoothing does. Smoothing takes the count of all the values, and there's a smoothing constant, and then you do a weighted mean between the proportion you computed and the global mean. Therefore, when a user shows up infrequently, you will set their target encoded value to the global mean, and when a user shows up more frequently, you will set their target encoded value to the proportion that you computed. Target encoding adds a new value to each row. This value comes from computing the portion of targets over a group of rows. You cannot use the same row in its own computation. Therefore, we use k-fold. We take all the rows of the training set and we break it up into 5 groups containing 20% rows each. Then, when we compute the target encoding for one group of 20% of rows, we use the other 80% of rows for the computation. This prevents leakage, and it makes target encoding generalize better to unseen data. In order to determine which columns we should target encode, or which combinations of columns we should target encode, we need to do experimentation. We need to create a new column and then calculate our model's validation score to see if it increased our model's accuracy. The code here demonstrates target encoding the column B user ID combined with language. If we do this using pandas on CPU, creating the new column takes 145 seconds. If we create this column using Rapids and GPU, it takes 1.27 seconds. Therefore, we observe a 114 times speed up using GPU Rapids versus CPU. This is crucial for creating an accurate model because we need to trial and error many features to find which features will give us the most accurate model. Target encoding was only one technique we use to create new columns. In our PDF paper, we list all the techniques we use, and in the next slide, I'll show you one more technique. One of the original columns was tweet text. You cannot enter tweet text directly into your model, so you need to engineer new columns from it. We handcrafted the following 8 new columns. The first 3 are numeric features: token count, tweet character length, and number of @ symbols. The next 5 are categorical features: first token, second token, last token, penultimate token, and tokens mentioned after the @ symbol. Another way to input the tweet text column into our model is use transfer learning. We input the tweet text into a pre-trained multilingual BERT, then use the mean pooling of the output layer as a new feature. These are tweet embeddings. Alternatively, we can fine-tune a pre-trained BERT using our 4 binary targets. Then we use the out-of-fold predictions as 4 new features to our model. The second approach was working, but it did not improve our model enough to justify the significantly high computational time. So far, we have discussed the advantages of feature engineering and accelerating our experimentation pipeline. Our experimentation pipeline is the creation of new columns and training and validating our model locally. I would now like to show additional ways to accelerate our experimentation pipeline. We have already seen how using GPU Rapids instead of CPU allowed us to target encode 114 times faster. I would now like to discuss how we can use multiple GPUs. Dask is a task-based library for parallel scheduling and execution. Using Dask, we can keep our code the same as it was before, which was written to operate on a single data frame, and then behind the scenes, Dask will partition the data frame into pieces and give each piece to a different GPU to do the work. Here is code demonstrating how to use Dask together with Rapids QDF. First, we load in the libraries. Next, we create a cluster and client. And lastly, we load our data frames in with Dask QDF instead of QDF. Afterward, our data resides in the 2 data frames train and test. And then the rest of our code is the same. We can use the same code as we did before, and Dask will automatically utilize all the GPUs on our machine. So for example, if we're using a DGX workstation, which has 4 NVIDIA V100 GPUs, then we observe the code will run 4 times faster and will have 4 times the memory available. The reason we observe 4 times versus 1 GPU is due both to the multiprocessing, but also the RecSys challenge dataset does not fit on a single GPU. So when using 1 GPU, memory had to be swapped out between GPU and CPU. Once you use 4 GPUs, all of the data can sit on the 4 GPUs. So part of our speed increase is also due to the fact that we're no longer transferring data between CPU and GPU. I will point one other thing out on this slide. Notice in the picture, the GPUs have 2 ways to transfer information between them. The top left GPU can actually pass information through the PCI switch to another GPU, or the GPU can talk directly through NVLink, which is a very high-speed data transfer. By default, Dask is using the PCI. So later, I will show you how you can use the NVLink for even more speed up. Similarly, Dask can be used together with XGBoost. Here is code to demonstrate that. Once again, it is very easy to do. First, import the libraries, then create a cluster and client. Then, when creating your XGBoost datasets and training and predicting your model, you just change the call from its original thing to now what you see here, which is xgb.dask and then the operation. When you do this, we observe, when using 4 GPUs, we observe that this performs 4 times faster than using 1 GPU, and we have 4 times the memory available. When setting up your cluster, if your machine has very fast NVLink connected between the GPUs, we can add additional code to take advantage of it and go even faster. The code on the bottom left is what we previously did to create a cluster and client. But now, if we use the code in the box, where we set the protocol to UCX, and we enable TCP over UCX, and we enable NVLink, then from here on out, Dask will utilize the super fast communication between your GPUs. When doing this, compared with 1 GPU, we observe it goes 8 times faster. You may think this is not possible. How can 4 GPUs go 8 times faster? But this is because the speed increases due to both multiprocessing, but also, if you remember, if you just use 1 GPU, the data was not able to fit on 1 GPU and it was swapping. So now we have 2 things happening. We have a 4 times speed up because of multiprocessing, and we have a 2 times speed up because we're avoiding data transfer between CPU and GPU, for a total of an observed 8 times speed up. If I didn't see it with my own eyes, I would never have believed it. A GPU achieved 280 times speed up. If you run our code end to end on pandas using CPU and some multiprocessing, it literally takes 11 hours. And then when you run that same code on GPU using Rapids and 4 NVIDIA V100 GPUs, it finishes in 2 minutes. It's absolutely amazing. In those 2 minutes, the code loads 160 million rows of a data frame from disk. It then creates 115 new columns using computationally intensive algorithms such as target encoding with smoothing and k-fold. It then trains 4 models and predicts 4 test sets, all in 2 minutes. It's absolutely unbelievable. This was the secret to our success. By creating features and training models so quickly, we were able to experiment and try out over 1,000 features in the last few months, and we were able to find which features made the most accurate model, and that model achieved first place in the 2020 RecSys Challenge. I'm so grateful to have this experience. Thank you, Twitter. Thank you, 5 organizers. Thank you, NVIDIA. Thank you, teammates. Thank you, everyone.
All right, thank you so much, Chris, for that great presentation, and to the rest of the NVIDIA team, and congratulations on the first place. So we have a few minutes left for Q&A. There was one question that was posed in the Q&A for all of you. So the question is, Do you have the chance to check if MF embeddings would further increase XGBoost model accuracy when added with other features, or would that make the feature matrix size unjustified with respect to prediction accuracy gain?
Okay, so I saw that question. I think that sprung up right before we showed the slide where we actually did build some models using extracted text embeddings, and it did using the BERT embeddings. It did increase our accuracy, but by default the multilingual BERT is outputting a vector of length 1024, so that's 1024 new columns. We had tricks to reduce it, but you can see that's a lot of. I mean, we originally had 100 features. You now want to add 1,000 new columns, and it was a very small gain. And we did tricks to reduce it, but in the end, we just decided. And then, of course, it made training and everything longer. So in the end, we decided it wasn't worth, for that small gain, it wasn't worth the extra time and computation to do that.
Great, thank you. A question that I have for the team is, so you said in the presentation that certain combinations of specific features indicated a person was going to like the tweet rather than not. And there's obviously a lot of different combinations if you're adding hundreds of columns and a lot of different permutations here. Did you test every single combination, or was it lucky that you just happened to find the top one?
So yeah, that's a common question that we hear. So it's a combination of both. So both. So we have a big team of 10 members. So a lot of it is human intuition. So a lot of the features are motivated by, we do lots of plots. So you plot, you basically combine columns and plot that on the x-axis and look at the conditional probability on the y-axis. And if you make enough plots, you say, wow, this interaction of features is very predictive. So some come from exploration and human intuition, but there's also brute force methods where you can just set up a for loop, which you're right, it just randomly combines columns. So both. And I'll add one more comment, which is, this is important to note, the original data set only had 20 columns. So when we discuss combinations of columns, we don't just make combinations of the original 20. So we first create an intermediate 100, which are not target encoding. We just take the timestamp, for instance, and we add a column day of week. We add, which is categorical, Monday, Tuesday, Wednesday, Thursday, a 7-value categorical. We add hour of day, 24-value categorical. So we already add hundreds of new columns, and then we basically do combinations of amongst these hundreds. So you can see there's tons and tons of combinations to check, and combination of brute force and intuition.
Awesome. Well, we are at time for this part of the session. So thank you so much, Chris, and claps to the whole team. And for anyone else who wants to hear some more from Chris, he will be one of our panelists in the final roundtable. So make sure you stick around for that. And thanks, up next, thank you, Chris. So up next, we have the paper Gradient Boosting and Language Model Ensemble for Tweet Recommendation from Pierre Guilabert and Santi Segui. And this will be a 15-minute video followed by a 5-minute Q&A. So again, for people who are just joining, if you have any questions, please navigate to that specific paper session on Whova and add your question on the Q&A section there. And I will go ahead and start sharing my screen. Can someone confirm that they can see this okay?
Yeah, it's okay.
Great, thank you.
Hi, my name is Pierre Guilabert, and together with the Professor Santi Segui from the University of Barcelona, we developed a model to participate in the RecSys Challenge 2020 edition. These are the topics I will talk about during this presentation. First, I will briefly introduce the problem and the data we used. Secondly, I will explain in detail the models we created and the features we used to train those models. Lastly, I will present our results, showing the performance of the final model. So first, let's talk about the problem. As all of you may know, the problem here is to predict engagement between users. So for example, in this case, we have to predict if Joe Biden is going to interact with a tweet written by Barack Obama. Reactions can be of 4 different types, which are like, reply, retweet, and retweet with a comment. We have a huge amount of data, well, a huge amount of tweets, which were sampled from 2 weeks of February. The dataset provided to us for the organizers contains positive and negative interactions between users, negative meaning that there is no interaction between them, Each interaction has information about the tweet, but also about the user who has written the tweet, that is the engaging user, and it contains also information about the receiver of the tweet, or engaged user. Now we will devote some time explaining our approach and how we created the features that helped us to solve the problem. Given a tweet, we could ask what information we can retrieve from it. For example, we know that text is important, but how about the user who has written the tweet? These type of features will be important for our model. If we focus on the text of the tweet, there are two things that we detected as important. On the one hand, we should define a metric to rank important hashtags, since having a trending hashtag could imply that this tweet will reach a wider audience. On the other hand, we defined an embedding of the text in order to capture similar tweets, that is, tweets that probably talk about the same topics. Then we could think about the user who has written the tweet. Different users may have different impact on Twitter network. Some could be really influential, and some have no impact at all. So we tried to design some features to represent that behavior. In the same way, we can extract features from the receiver of the tweet. There are users that only that only react to the accounts they are following, users that only give one type of interactions or other behaviors, and also previous interactions between users are important when trying to predict future interactions. Lastly, from the given dataset, we can extract several features that we also used, such as the language the tweet is written in, the media elements that it contains, such as images, videos, or GIFs. And here we can also include the text features. In our case, we decided to use a BERT model to be able to represent the text of the tweet. The most important relevant features of this slide will be explained in further detail later on. So some of you may know BERT model. We had read it before, but we never use it. So it was very exciting for us to work with it. BERT is a huge model with 12 fully connected layers with extract structures called attention patterns. We used it from a fantastic implementation and the Hugging Face library implemented in PyTorch, where it is very easy to load pre-trained models and add new layers or personalize it in many other ways to fine-tune it for a specific task, in this case for this challenge. So this is our language model. We added 2 new layers at the end of the BERT model, and for each of these layers, we extract one output. The first layer, which is a dense layer of 50 neurons, was used to create an embedding of the tweet. And the last layer, with just 4 neurons, is the layer we used to output the target probability. In this case, these last outputs targets the real ratio of engagement for each type of interaction. For example, a tweet that appears 10 times in the dataset and only has 1 like reaction will have a real ratio for the like class as 1/10. To train it, we use a mean square error as loss function between the real engagement ratio and the predicted one. Now I will talk about all the features we created. These features were combined with the language model output to be able to train the final model. First, these are the features we extracted from the tweet text. Since this is a brief presentation, I will not talk about all of them. I will just point out that some of them were grabbed into buckets using the formula below. This replaces the exact value with a representation of the bucket where this number belongs. For example, in the case of text length, we did not keep the exact number of characters of each tweet. Instead, we grouped tweets with similar lengths into the same buckets. Here we can see in gray features that were obtained from the original dataset and were slightly modified and one hot encoded, so they can be inputted to the final model. But I won't talk about them. I will just focus on the hashtag popularity since it is one of the most relevant features. Hashtag popularity was one of the best features we created for the challenge. It consists of a ranking of hashtags from past tweets, and two different rankings were computed. On the one hand, a global popularity of the hashtags, where all hashtags were taken into account. That is, the hashtag that appears the most in the last 2 hours has the maximum rank. On the other hand, a local rank where only the tweets in the same language are considered. Here, we also used tweets only from the last 2 hours. In the case of tweets that contain more than one hashtag, the hashtag with the higher rank is what we used. Then we have the engaging user, that is features related to the account who wrote the tweet. As before, there are some features that were slightly modified from the information provided in the original dataset, but there are two features we created, engagement and popularity, that we would like to explain further. First, engagement. We defined engagement between two users as the number of interactions between those users over the total number of interactions. We can see that this is a two users metric. It means that we need both users in order to compute it. And this feature was the one that turned out to be the best of all. We called it popularity of a user because it only affects the user who has written the tweet and how this user impacts on the network. It is computed as the number of positive interactions over the number of total interactions. And for example, a user that always receives like interactions in all of his or her tweets will have a high popularity for the like class. I will not repeat the same features for the engaged user since they are roughly the same as in the engaging user, but there was an extra feature we added for the engaged user, that is language reaction. Imagine that a tweet written in Chinese is shown to an account that never interacted with a Chinese tweet. So this feature controls this type of behavior between languages where negative interactions are identified. To combine all these features, we used a light GBM classifier, which is very well suited for this task because it is very fast to train and it is very well addressed for large data sets. We created 4 different models and we trained each of them to predict one of the 4 targets. We used binary cross entropy as loss functions, since it is very related with one of the metrics we used to evaluate our submissions. Well, the authors of the challenge used to evaluate our submissions. And finally, this is the model architecture that we used to generate the best submission. We can see at the bottom of the 4 types of features we have just explained. We can also see the language model with its 2 different outputs and how all these features are inputted to the 4 classifiers, one for each target. And then this predicts the final engagement probability. Furthermore, we bootstrapped the dataset 3 times and we used it to average, and we averaged these outputs to predict the final score of probability. Some results. Here we have some of the most relevant parameters of our models. Regarding the language model, we fine-tuned a BERT model for just 3 epochs, since in the 4th one it became too overfit. Also, authors of BERT recommend to fine-tune it for 2 to 4 epochs. We also used Adam Optimizer and a very small learning rate. About the light GBM classifier, we trained all the models for 1,000 epochs, and we used early stopping to avoid overfitting. We also used L1 and L2 regularization, and we limited the light GBM trees expansion to 10 levels and 70 nodes. Here we can see the results we obtained in both validation and leaderboard sets. We created a validation set by splitting the tweet IDs into 2 groups, one of them containing 90% of the tweet IDs, and it was used to train the models, and the other one with the remaining 10% for validation. This way we ensure that a tweet is not repeated in both train and validation sets. Since LightGBM is a tree method, we can easily extract the best features of the models that is, the features that the model decided to use when training. We can see how popularity features and text-related features turned out to be the most relevant ones for the four models. And with all of that, we obtained the 9th rank of the challenge. So we are very happy because we did not end up in last place, properly earning our team name, and because it was my first time participating in this format of challenge and my first paper submitted. Thank you very much for your attention, and if you have any doubt, I will gladly answer.
All right, thank you so much. And Pierre, there you are. So we have Pierre here who to talk with us about the paper. So if you have any additional questions, feel free to ask them in the Q&A section, but we'll start off with one that was already asked. So someone asked, the model is bootstrapped multiple times and the final prediction is computed as, oh, sorry, I'm reading the wrong thing. So the question is, your final ensemble had 3 models. Model 1 seems to have a much lower performance. Can you describe what additional signal this model provided? Why did you ensemble a much lower performing model with the other 2?
No, it just, we bootstrapped the same model 3 times and we use it to average. We averaged the results of the 3 models to predict the final one, but they are the same models, all of them.
Great, thank you. And a question that I have for you is, while we're waiting for other questions to come in, so it looks like you selected some interesting features like hashtag popularity and others that weren't used by other teams. So what led you and your team to think of using different features like that?
Hashtag popularity was one of the text-related features that we thought we could use because it was very significant for us when analyzing the dataset that tweets with the same hashtag usually appear in the following tweets. So we decided to analyze hashtags because we hope it was a great feature.
Yep, and it made you not finish in last, so that was good. So another question from some of the chairs of the workshop. So since you are one of the last presenters of the workshop, you might have a clearer idea of what some of the other teams did. And since there are other teams that also adopted the light GBM model, can you think of an approach that could maybe be combined with yours that would have helped you improve your results now knowing what you know?
Yeah, we had a lot of ideas in the beginning of the challenge, but because of the lack of time and resources and all of it, we could not implement it. And there are some groups there are other teams that implemented things that we thought at the beginning. So we are very happy to see that they well properly could work, no? And I don't know, maybe some ideas of other teams could be implemented to improve our model.
Since we have a little bit of extra time for questions here, you did mention that this is your first time contributing to the challenge and trying the challenge in your first paper. So do you have any advice for other people who might be watching right now who are maybe looking to do the challenge for their first time next year?
Yeah, some at the beginning is very hard to begin with the challenge because of there is a lot of data and it's very hard to begin to work with it. But if you focus with, I don't know, maybe a lot of attention, it's nice to see the solutions improving.
Great. And did you run into any interesting challenges or anything unexpected, especially given that this was your first time trying this out?
Sorry? The first one? The first part?
Did you run into any challenges or anything unexpected or any roadblocks that really were like particularly difficult?
Yeah, data and resources, because in the university we have only one server dedicated to the challenge, and it's not very powerful. So we decided to move to the cloud, and yes, the major inconvenience for working in this challenge is the huge amount of data we have here.
So on that note, actually, do you have any advice for other students who maybe only have university resources and who don't have large machines with lots of GPU and CPU power if they're looking to work with a lot of data like in this challenge?
Yeah, at the beginning we started with very few data, and it was not that bad. So you can work with less data and present a decent submission. So it's possible to perform better with few data if you know what you are doing.
Great. Well, it's really good to know that that's possible, and thank you for showing us that. So just double checking if anybody has any questions. If you don't want to add them in the Q&A, you can also take a moment to unmute. We do have an extra minute or two right now, just in case anyone else has anything they'd like to ask. All right. Well, then, thank you so much, Pierre, and thank you to the team. Wonderful work. And up next, we have Dietmar, who's going to be presenting our final talk today before the panel. And this is the talk for why are deep learning models not consistently winning recommender systems competitions yet. So Dietmar is sharing his screen, and whenever you're ready. Just make sure you unmute yourself before you start.
Thanks for the unmute, finally.
There you go.
Got me. All right. Hello, everyone. So, yeah, this is why deep learning models not consistently winning recommender system competitions yet. I'm Dietmar Janach from the University of Klagenfurt in Austria, and this is joint work with Gabriel Morera and Evan Aldrich from NVIDIA, and one of the winning teams. And both of these colleagues work on recommender systems at their company. So congratulations for winning, and congratulations to the other teams, and also congratulations to those who successfully participated in this competition. Okay, there's not so much to say there about the big success of deep learning and this background story. So we really see in the past years this huge success of deep learning technology, and it's really the method of choice everywhere, and of course also in the recommender systems literature. And if you look closely at this, you see for all the particular algorithmic tasks that we have in recommender systems, so we have rating prediction, personalized ranking, predicting the next item or basket, learning representations of users and items, encoding site information, combining different types of information hybrids, building conversational systems, attacking recommender systems. Everywhere we see people using, in academia, using deep learning. And as a disclaimer, this is not in no ways anti-deep learning or something. So we also use deep learning technology in our own research. So, and when we look at the academics, I work in academia. So if you look at the academic literature in the past few years, deep learning methods are almost always better than everything that we had before. And today, nobody seems to use any of the techniques that we've seen before, like matrix factorization, learning to rank, decision trees, random forest, nearest neighbors, logistic regression, SVMs, GVMs. So nobody uses them when they propose a new solution or some progress in the field, except these methods are only used to show, okay, we have deep learning models which are better than these baselines that we had years before. So, and deep learning are so good that they even outperform other deep learning models nowadays. So that's really good. So in some ways, when we heard the opening statement saying, okay, maybe deep learning is not good for recommender systems. So looking at the academic literature, this is there's no evidence for that. So we only see more or less deep learning models for everything that's published. And there's also a lot of success stories from industry. So again, there are many published reports about the success of deep learning for recommender systems. We have Alibaba, Baidu, Google, Pinterest, Facebook, YouTube early on, and maybe many, many more. So there could be different reasons why deep learning is so successful there, but there's these reports. So it seems to be there's no doubt that deep learning works both in the academic world and in industry, right? But then here's the question. So who wins in the competitions? And if we look at the winning solutions from the last 3 years, from 2017 to 2019, so deep learning is here for a longer time, it's not deep learning or not deep learning alone. So we see substantial feature engineering. So maybe there's a lot of domain knowledge people put in, or as we've seen just previously, there's a lot of automated trying out, brute force, finding what good features might be. And then we have gradient boosting more or less as the final model that makes the ultimate prediction. And for those in academia, at least, who don't know these ancient technique, it's from the late 1990s at least, and it's based on building ensembles of weak learners. And as we just seen, who wins in 2020, it's substantial feature engineering, also with some innovative ideas, as we've seen, and a lot of engineering also on the speed up things and trying out a lot of things. But in the end, it was gradient boosting. And of course, we've seen other papers here that tried out deep learning. We've seen the second place solution who said, okay, we used the language models, and this seems to be a place where it works. But also other papers were there in the previous competitions where there were combinations of deep learning, but it was never just a winning model, okay? So now we have this discrepancy, I would say. At least I see this discrepancy that we see academic literature. This is what interests me, where I can oversee the field, and the competitions, and maybe real world. So there we have 3 hypotheses that we developed, which could be reasons. So are the problems different? Are the researchers different? Or is the way we evaluate, is that really different? So let's start with the first part. So are the problems different? So we can compare let's say the academic setting and the challenge setting. And let's assume at least that the setting and the challenge is closer to the real world. So think of movie lens dataset is often used in academia, but the challenge datasets to come from industry, and we might assume that this is really reflecting the needs of the industry here. So first question is, okay, dataset sizes. So we've seen the dataset sizes are large, like in this year's competition, which already leads to some challenges here. And we've seen even more interactions, 320 million interactions from Xing. And so we can say, okay, this is not so uncommon in academia. So we have Netflix here from 2006, where we had 100 million ratings. So, okay, we're used to handling larger data sets also in academia. And here's some interesting points here. So when we look at the papers that are published in academic research, we often see very, very small data sets. So we see in 2019 or 18, we see papers said, okay, we evaluate the movie as 100K, and sometimes even smaller data sets after pre-processing. So this is surprising in some ways, because in principle, deep learning is said to profit from large data sets. And so it's surprising that in academia, at least, deep learning works very well on these tiny data sets and seems to outperform all the other methods, even so there's not much training data to learn. Looking at the competition setting, there could be a challenge, of course. So when we have deep learning can profit from large data sets, in the competition setting, it might be difficult to have all these giant data tables somewhere in memory, and this might hamper the use of deep learning in these competitions. There's another difference, a potential difference regarding the data sets. So we see these data sets are large, okay? But sometimes, at least some of the data sets, they're collected within a very small time window. So there's just a few days, you collect all the traffic on some commercial website, you end up with 100 million interactions. But in the end, it just covers a few days because these large websites have so much traffic. But in reality, when we talk about real-world deployments, where deep learning seems to work quite well, the datasets maybe have rich interaction history. So you have one user who comes, visits the site over months or maybe years, So there's many more interactions that you might observe for each user, whereas when you just sample from a few days, you might end up with a data set which is where it's difficult to learn or find an embedding for a user. Okay, so one hypothesis here could be that deep learning, the success of deep learning in practice might be there just because the advantages of deep learning only unfold once you have more data available for training. Another difference that could be a reason for the discrepancy is that prediction problems are different. So in academia, historically, we have these user item rating matrix, like a movie rating data set. We have long-term user profiles. We have many interactions per user. And what we do is previously we predicted ratings. Now we rank the items. And looking at the challenges of the previous years, the settings were a bit different. So in 2015, we had like session-based recommendations. Also last year, it was sort of a session-based thing. And it's really a bit different. And if we look at the deep learning and session-based recommendation, there are a lot of papers out there. And but still, if we even in academia, we see that when you compare deep learning models for these sparse setting with very trivial nearest neighbor techniques, it turns out that deep learning models are challenged, at least in those cases where you don't have site information that can be leveraged. Okay, so this is one challenge. Okay, so we have different problem settings in competitions, which might be a problem. And in challenges, we often have site information, so features, whereas in academic papers, often it's the entire research problem is operationalized to just have user item rating matrix, because as soon as you add content in academic papers, comparability is limited because nobody uses the same type of site information, right? So that might be a difference as well. And finally, there are different metrics used in the competitions. Sometimes they're often just created for the challenge. Moving on to the second part is, are the researchers different? So this is a quick one. So we could say develop some hypothesis saying, okay, the researchers are not expert in deep learning. These are the grandmasters. They just use gradient boosting because they did that last 10 years. We can hypothesize they don't have enough hardware. And this, okay, might be an issue for many participants. Or we just say, okay, the participants are experienced in all these competitions, they just use gradient boosting because it worked in the past. That's a safe thing. But when you look at the participants and the winning teams, it's difficult to maintain the first two hypotheses because we have obviously a lot of expertise in deep learning, and we also have people who have access to the resources, and still not the deep learning models are the winning ones, right? Another perspective here is that the researchers might be a bit different. So the contestants, the participants in the challenges, they have different objectives, preferences, and work process, right? And we speculate that gradient boosting might have some advantages in this process, like there's stable to overfitting. There's some other aspects that we can take into account here. Whereas on the other hand, neural networks sometimes really need more care, tuning, and maybe their hyperparameter changes have more effects. And this, in combination with the short durations of the challenges, might be an issue, so that you cannot try out so many different things before submitting the final result. Let's move to the final part. It's about, is the evaluation methodology different? And here we could also ask the question differently from the talk. Why are deep learning models always winning in academia? Which is not the exact opposite, but it is somehow related. So here, there's a clear yes, that the evaluation process is largely different. So we set up a list of differences. So we looked at how the evaluation is done. So these are questions like who selects the data set for benchmarking, who selects the baselines and who optimizes the baselines, who picks the metrics, who determines the specifics of a protocol, like cross-validation, target item selection, who does the measurement actually, right? And who publishes it, who sees the test data, and so on. So, and we see, just looking at this column, we see there's a lot of freedom here for academic researchers, so they can pick many parameters of their experimental design. So, and often before publication, the researchers are the only ones who evaluate their own model against the baselines, right? And On the other hand, in machine learning competitions, there's not much flexibility here. And we've seen also, like in academic research, as we see the test that there was a paper this year at RecSys showing that a substantial fraction of papers reported that they optimized the hyperparameters in the test set, which is of course not possible in a competition, right? So the question is, are these differences responsible for what we see, that in academia, deep learning always wins with few exceptions, whereas here they're not winning yet, right? So, and we've seen other parameters that might influence that. What we know, of course, is that this freedom in academia is important. So we need that flexibility to explore new questions. And of course, we know there are certain, the problem is of these freedom of selecting the experimental configuration is that this might introduce a lot of biases, most prominently the confirmation bias. So you'd only try to, your hypothesis is that your model is the best, right? And so you look for evidence that, that your hypothesis is true. And this is also a problem here that comes with the freedom that is needed for academic research. Okay. And we've seen that there are evidence, there were papers this year comparing matrix factorization with neural collaborative filtering. We did a lot of research last year publishing results that show that there are some, these biases come into play, that optimization of baselines is not properly done sometimes, and then we don't have these wins are not really there. Let's move on. So I have 30 seconds to move on to discussion and conclusion. So we found this is an interesting question when we saw the results in academia, when we see the results in challenges, and we try to understand what the reasons are. And we don't have a clear answer yet, but we should investigate potential problems that we have. What we think is that there's a lot of potential that is not fully exploited yet. That's the positive message of this talk, saying, okay, these deep learning models, there are some problems why we cannot apply them yet in competitions. And maybe there are some opportunities for research here. Of course, typical research goals could be better combining different information sources, and maybe we need better toolkits that are just easy to use, like for other things. And for the side of the academic research, I think we should not forget to what was working well 5 years ago and forget about non-deep learning methods in academic research. All right, and I will conclude here. Thanks for the attention, and I'm happy to answer your questions.
Great, thank you so much. And thank you also for submitting a paper about the challenge that wasn't just from a challenge submission. So as a reminder for everyone who is just listening in on the session, if you have any questions for Dietmar, feel free to put them in the session Q&A, which you can find if you click on the actual session link in the Whova. We have about 5 minutes for Q&A right now before the final panel. So the first question for you is, because you mentioned some of the differences between data sets that tend to be used for challenges as opposed to data sets that are used in industry, something that I'm wondering is if you think, if we're trying to make challenges more closely related to things that we're going to be using in industry, do you think it would be better for us to choose a data set that has more user profiles, but it is collected over less time? Or do you think it's better to have a data set that is collected over more time, but with less user profiles if we only have X amount of data?
I think there's both things are possible. I think it depends a bit what's the, what I would find interesting. It's a subjective thing. What I would find interesting if challenges very closely reflect the problems that companies face. So if the companies face the problem, okay, we have a sparse data situation, here we go with a data set like this. But if we have longer profiles, just share them if possible. I remember for news recommendation, we've for many years seen just data sets from, I think from Yahoo News, like 3 days of their front page traffic. And this is difficult to learn some things here. So it's not a question of what's good or what's bad, but it might be the reason that because in recent years we have these data sets that only cover a few days, that this prevents deep learning models from winning.
And actually, just kind of a follow-up to that, the more data that is allowed in a competition, or the more data that's given in a competition, even if it does make it a little bit more relevant for what is actually happening in industry, that does make it less accessible to some people because they won't have access to large amounts of hardware. So do you think that it's possible to win a competition like this without having access to hardware like people who are in industry do?
Yeah, that's an interesting point. Yeah, and that's really, I think that's true. So then if you blow up the data sets, then academic researchers will drop out, or many of them will be discouraged to do something. So we probably need to find a smart way to have maybe longer individual profiles, but fewer interactions in total, because this is really a problem for, like, we participated in previous years, and my PhD student did also all of the work. We had limited resources. We used nearest neighbors to end up in the top 5, but then we could do a lot of features because it just didn't fit into our memory, and data sizes keep growing. Yeah. It's difficult, I don't know.
Definitely. We have a question from the audience. So the question is, does this difference between challenges and academic performance happen similarly in other areas such as computer vision, Kaggle in general, or otherwise?
I don't know, sorry. So this is, we didn't look at we looked at a few other related domains, but we didn't do a systematic analysis. But my impression is that, of course, we know there are some problems like image and language where deep learning just works well, but it seems there might be other machine learning, applied machine learning areas where we might see similar patterns.
And one final question here is, how do you think this will be affected by reproducibility papers?
What would be affected?
It just says this, but I'm assuming the lack of deep learning models being used for competitions.
I don't know if this is a huge impact. So the competitions go as, so people will try whatever works for them. So this will be not impacting, I think, competitions. In some ways, I hope that papers like this or these insights have an impact on academic research, where we seem to be forgetting about other simpler models too often, and trying to have the latest, more complex models there. I'm not sure it will have an impact, but I think it's worth looking at simple techniques as well.
And we'll ask actually one final one here. Do you think that, speaking of the discrepancy between academia and challenges, do you think that the difference between those two will get smaller over time based off of what you know?
I think it's a dynamic thing. So the challenges develop. I think the challenges learn, the settings for the challenges will change. I have a bit of a fear, like we've seen this last slide on the evaluation methodology, and I fear we have this sort of biases. We observe that we want to see our models win, and we have trends, of course, in academic research, and so I hope this discrepancy will disappear, of course.
Great. Well, thank you so much, Dietmar. And you're actually one of our panelists, so you'll be sticking around. And for everyone who is here, we are now officially at the last portion of the workshop. So virtual round of applause to everyone who presented. Thank you so much for the amazing papers and the amazing submission and work for all of the teams who participated, even those who did not present today. And if you are a part of the panel, if you want to show your video, if you would like to do so, I'm going to briefly introduce everyone. So for anyone who doesn't know who I am, I'm Jessie Smith. I'm from the University of Colorado Boulder. I'm one of the academic chairs for this workshop. And on this panel, we are also going to be chatting with Dietmar, who is representing academia, and he is who you just all heard presenting on this last paper. We are also going to be chatting with Chris Deotte, who is a representative from the winning team at NVIDIA, and Max Volkovs from Layer 6, and they were the second place team, as well as Luca Belli and Wenzi Shi, representatives from the Twitter team. So hello, everyone, and welcome. The way that this roundtable panel is going to work is we have a few questions lined up, but for anyone who also has any questions for this group of people, feel free to include it in the Q&A or the chat, and I will try to stay attentive and ask those as well. And then for the panelists, if you have anything to contribute, just simply unmute yourself and say what you'd like to say, share any thoughts that you have. And we're gonna start it off with something that I think a lot of people are wondering today and have been wondering for the last few months. There was a little bit of a scandal in this year's challenge, and that a lot of people were talking about a data leak. And there's been a lot of confusion about whether or not there actually was a data leak. So maybe Luca or Wensi, if you want to go first to kind of clear up any confusion. But I think in general, everyone would love to hear thoughts from participants about what your experience and thoughts are on the issue of the data leak in general.
Luca, you want to go first?
Yeah, sure. Hello, everyone. Sorry, I had problems unmuting. So yeah, I think maybe we should have done a better job clarifying this point, or maybe even before the challenge started. But every piece of data that is actually in the challenge data set, it's already public. As in, you can, just go to the API, connect, and see the exact same data. And I was mentioning this morning, actually, what you can get from the API is more. So the dataset challenge, it's a subset of what's publicly available. So in that sense, I think that's different from, other in the past, where similar challenges were organized and people were able to sort of like reconstruct private attributes of users by looking only at the public one. So in our case, there was everything was already public. So we were aware that, by just scrambling the user ID or using, not publishing the text, it's not an effective privacy preserving technique. So we were very aware that people will be able to reconstruct immediately. We decided to do that just to prevent zero effort misuse of the attack. Or sorry, zero effort misuse of the data set. I don't know if this clarifies or confuses things even more.
And from the panelists who are from the people who did the challenge and participated, are there any thoughts from any of you?
I can add a comment. I think, so, early on, it was certainly concerning being a member of this competition, knowing that, potentially our competitors, could take advantage of a leak. But I think it's great that the organizers made it a requirement that you have to post your code. So, all the winning solutions are posted. So, all the code is reproducible, which shows that the code on its own uses only the columns in the provided data set, and the code's not going out and scraping data off of Twitter, finding the original post exactly. So I think making the code need to be public, I think really prevented anybody from exploiting that leak.
Yeah, that's what I'm going to say. So we actually not thoroughly, but checked all the submissions, and we didn't find any obvious usage of data outside the dataset. But as I said, the code is actually submitted, and I hope it will be open sourced by all the winning solutions. And everybody could examine the code and actually try to reproduce the results. And in one of the rules, if we do find people that's actually using the leakage instead of just using the data set, then they obviously would be disqualified, even in the future.
So I had a side comment. So this is not so much on the leak. What we found in the challenge is that if you generate an all zero submission, it scores really high on AUC, but really low on RCE. And so I think there's what we observe in the test set is that several teams in the top 10 and even in the top 5 have actually exploited this to get a high average by just scoring high on AUC. So I think this is something that we should probably watch out for. I think this was happening because the function which was doing evaluation just scored ties in a favorable way. And That's one of the issues that I kind of observed aside from the leak.
Yeah, that's a valid point. I mean, we're happy in the end, nobody was actually using that to win the challenge in the first 3 places. So we didn't actually expect that, but if we were to do it again, I think we're going to improve the evaluation metrics. So actually, if you score high in one metric, but really low in the other metric, you'll get a lower overall score instead of currently the average. But this is definitely something like for the future lesson that we could learn for.
Great, and any final thoughts on this topic before we move on? All right, so now let's reflect a little bit on this year's challenge. And this is a question that's actually from the Twitter team, so directed more at everyone else. But what was missing this year? If we were to do this entire challenge again, what would you like to see differently? And what do you wish had been done differently? As well, for those who are listening, if you have any thoughts on this, feel free to add them in the chat too.
So I can jump in. I think it would be helpful to have the raw tweet text because we used a lot of language approaches, as you've seen from our presentation. And we found that since we had only tokens, we did reverse them back into the raw representations, but we lost some of the more rare occurring ones. And so I think just releasing the raw text in the first place would have been really helpful.
That was something that we actually discussed a lot before, as you can imagine, and should we or should we not? And then we decided for not to do that, for sort of, again, try to make not as obvious to figure out, what was the original data point.
So may I say some things I didn't, sorry. Chris?
Oh, I mean, you can go first and then I can make a comment afterwards.
Yeah, that's now only an academic vision I would have. So I understand it's a machine learning competition, but recommender systems is more than machine learning, right? And predicting the past. Of course, I would dream of a competition where we could, at least in some ways, or some parts of what is predicted is shown to some users at some stage. I think we had that in other competitions, but I understand it's difficult.
That's actually an interesting idea, and actually, maybe to your surprise, but honestly, we were discussing it's way much more complex system to build. So eventually, we might actually get there. We're actually discussing what are the feasibility and the possibilities of doing so. But you could imagine it's actually going to be very difficult to implement, as well as respecting users' privacy at the same time. So yeah, this is definitely something we actually discussed internally and may or may not happen in the future.
So I could say something on behalf of one of my teammates. So we had a large team of 10 and everybody was focusing on different things, but particularly one of our team was really focusing on creating user embeddings. So looking at, the history of the user and really trying to chart the user, sort of the profile of the user. And I don't know if he's in the audience and can unmute Chalk, but I could try to summarize, but I won't do it as good a chance. But I think he noticed that many users, maybe millions of users, only showed up a couple times in the data set. So it made him it made it very difficult to try to use a feature such as user, like a user profile. And he actually created a lot of embeddings using, alternating least squares, a matrix factorization technique, and we put those embeddings into our boosted tree model, but they weren't helping that much. And he suspected it's just because we had such a large number of users that showed up once or twice that sort of other features, simply like follower count or other features things about the tweet end up becoming more important, and the focus was less on the user because we just didn't have lots of user data.
That was actually an artifact of the way we sampled, right? Because it was being a random sample, majority of users don't interact that much probably.
Yeah, I agree. Yeah, it's nice to say, for someone to say, oh, it would be nice if we had this, but I realize that your task is extremely difficult to put that data set together. So yeah, I don't necessarily, have a solution. If you just, for instance, just removed every user, if you just removed every user from the data set who shows up less than 100 times, you're saying that could, like you just said, that can have all sorts of other artifacts and, potential things that, could actually, that we may not want. So I agree, it's a difficult challenge.
Yeah, especially because then you would give out more information about the user that are actually in the data set, right? Because then you would have, you could learn a meaningful embedding about these people, right? And so is it okay to do it? I don't know. So again, for this year, we decided it was not okay to do it. So it was like just random sample. And yes, I agree that there was a lot of sparse signals from a lot of the users.
Yeah, and I'm certainly in no way complaining. I'm just answering the question, what could have been done differently. But I loved, the data set was fantastic. It was a lot of fun to explore and build features. There was, tons of great stuff in it, obviously.
Thank you.
Thank you for that segue, Chris, actually. That's very fitting because we're going to now transition from the things that could have been done better to the things that went really well. So for all participants, including those who are part of the organizing committee and the Twitter team, what are some things that went particularly well this year? And also, what are some things that maybe made this challenge unique and separates it from other challenges in the past?
I think for our side, obviously it's the size of the data, and I think the content features that we released, basically the bird tokens. What surprised that we actually did internal baseline before we released the dataset, because we wanted to test the dataset and make sure we're not releasing random rubbish. Because you can imagine we just sampled and we only have 10 features. Maybe nobody could ever build a recommender system out of this. So we actually tested internally and we got like 5 RCE. But to our surprise or delight, we saw participants like go way beyond 5 RC very quickly in the first months, and NVIDIA actually won by a big margin, which actually means there are some information in the data set and it was not a total failure.
Yeah, I'll respond to that right quick. It was, you're right. The original data set only had 20 columns, but there was tons and tons of things. A really creative feature that one of our team did was you can actually look at when you have a row of the data set and you're looking at a particular interaction, you could look in the past 1 hour, how often was that person online? So is that person, really active or not? And that's, one example, but we were able to just, from those 20 columns, we were able to dig out hundreds and hundreds of more ideas. So there was tons of signal in there, tons of signal.
I'm going to second that also. So having done actually 5 RecSys challenges in the row now, this was, I think, by far the largest dataset so far. And this was really exciting to us. We really had to optimize our pipeline to be able to iterate and train quickly. I think the other exciting aspect was the tweet content and the fact that it actually came in over 50 different languages. So this kind of maybe made it challenging to do feature engineering on that, because you really have to know each language. And so that was like this extra challenge that came with this large scale data set, which was really exciting to us.
Yeah, I could say, yeah, I guess I'll say what I like most. My comment earlier was just sort of a response, but yeah, the same thing. What I like most was the size of the data set. So I've been doing data science for a number of years, but I've personally, so I didn't do RecSys last year, but personally, I've never dealt with a data set this large. So it was a completely new experience for me. I always had, data sets with thousands or maybe 1 million rows. I always do it on my local machine with a CPU. But this data set, my local machine, I try to load the data, my local machine crashes. So I immediately had to look for new ways. I had to do, all the processing had to be done on GPU. Otherwise, you'd sit there for hours. So it was a whole learning experience for me. It was actually my first time, using the Rapids GPU data frame library, and that was for me the most exciting aspect, dealing with how to deal with a large data set.
Great. Well, there's actually a question from the audience, and this is just for the Twitter team. So the question is, will Twitter be using a tweet engagement prediction internally? If yes, why?
Luca?
Sure, or whatever. So one thing to mention is that obviously the data set we have internally has a bunch of extra features that were not released. Therefore, it will be hard to just plug and play any of the models that have been part of the challenge or trained for the challenge. And the other very big constraint that we have internally, but again, was not present in the challenge, is latency, right? So on Twitter, everything has to happen really fast. And we haven't checked any of the model for speed for latency. And so that, unless the winning methods are able to sort of like produce a result within our very limited time, it's unfortunately a no shit for us. But we did learn a bunch of new ideas and a bunch of techniques. I don't know if Wendy wants to expand on that.
Yeah, I guess Luca is more answering that. Would Twitter be using any of the models that was used on this data set internally? I guess the answer would be no. But the question maybe is asking, I'm not sure what the question is asking about, I'm just speculating. Maybe the question is asking about, would Twitter be using, or why would Twitter want an engagement prediction model in the first place? Actually, we do have engagement prediction model. As I said in the introduction session, that the reason why we have that is because Twitter wants to serve public conversation, which means that we want to find the right conversation for you at the right time. Which usually means that from billions of tweets that's tweeted every day, we want to find out the 50 most relevant conversations for you. And that's why we use the engagement prediction internally. And we do actually do that internally in order to find the relevant tweets for you. I don't know that which kind of answer the participants was actually looking for.
No, that's really great. Thank you. And just to kind of conclude this roundtable, maybe if all of you want to provide just like a very brief, in one sentence, if you had any piece of advice to give to people who want to do this competition next year, whatever the competition is going to be, what would that one sentence piece of advice be?
I would just jump in and start trying things. I did my first Kaggle challenge about 8 years ago, and I haven't looked back since.
Yeah, I have two sentences. One sentence is definitely use a GPU. Don't try to process this data set on a CPU. And then my next sentence is what Max just said. It's always intimidating. I've been on Kaggle a lot in competitions. It's always intimidating, but just make a submission. Submit all zeros, or take the original data set and only use 5,000 rows and build a little quick model from that. Just do something and make a submission. And once you see your name on the leaderboard, and once you realize you can do it, then it'll motivate you to keep working and keep digging and making a better model.
Also be patient. Like, I feel like things never work until they start working. There is no like, I don't know, sometimes it's just it's a step function. So I guess, as Chris said, just do stuff and keep iterating.
Yeah, I guess my advice would be find teammates. Actually make a team. But you can start alone and then you can find people and team up, and that will make much faster progress. I saw one question people asking, Twitter have open positions for internships. Yes, we have. Are there advantages for the participant for this challenge? I guess it will, like, you will pass the screening process faster, but then you will still do the same interview as everybody else.
Any word of advice from you, Dietmar?
I think things were said. I think start simple, start fast, find friends, good ideas, be creative.
Awesome, great summarizing. Well, it looks like we are at time now. So again, on behalf of all of the academic organizers, the sponsors, the participants, and everyone and this panel, thank you so much for providing all of your thoughts. And thank you everyone for your engagement and your participation in this year's challenge. This was really fun, and stay tuned for more news on next year's challenge. But for now, this is it for the 2020 challenge. So thank you again, everyone. And this concludes the workshop.
Thank you, Jesse. Thank you, Twitter. Thank you, all the organizers. It's a lot of fun.
Thanks, everybody.
Thank you.
Thanks. Bye.